Warm welcome and good morning, everyone. A warm welcome to our Honorable Chief Minister, Dr. Pramodji Sawant, and all the other dignitaries. I would like to request you to just look into your watches or into mobile phones for a second. We are on time, and our punctuality reflects the discipline and respect that such meaningful event deserves. Can we give a big hand for all of us? Starting on time sets the right tone for the entire day. Good morning, everyone. Respected dignitaries, dear scientists, teachers, students, and all the science enthusiasts present here and all other 8 venues, government officials and press media who've gathered here for Manohar Parrikar Vidnyan Mahotsav. It really gives immense pride and pleasure to Department of Science and Technology and Waste Management, Government of Goa, to welcome you all here to Manohar Parrikar Vidnyan Mahotsav. Every year, it's being celebrated on the birth anniversary of a visionary leader, an engineer by mind, and a statesman by spirit, Manohar Parrikar ji. Today's program is not just a celebration of science, but a tribute to a leader who truly believes that scientific temper is the foundation of a progressive nation. Once again, a warm welcome to each and everyone, and I invite Shri Jose Manuel Noronha, sir, to deliver the welcome address and overview and set the tone for today's Vidnyan Mahotsav. Sir, please.
Very good morning to Honorable Chief Minister, Dr. Pramod Sawant, Dr. Anil Kakodkar, Dr. Kiran Kumar, Professor Naval Gund, Professor Kaushik, Professor Venkatesh, Dr. Aniya, Dr. Sriniketan, Dr. Roy, Professor Tilvi, Dr. Ravi, Professor Yogendra, Dr. Iyer, Dr. Sasani, Professor Dar, Dr. Tiwari, Shri Vijay Mohan, Professor Josh Thomas, Dr. Sai Gautam, who is our Manohar Parrikar Yuva Science Awardee, Professor Uma Shankar. These are all speakers who are speaking at the different venues across the state of Goa. Manohar Parrikar Vidnyan Mahotsav began in 2019. So if you see the slide here, this is when the vision of Mr. Parrikar, when he first had a Nobel Prize series in Goa in 2017. These are some pictures of events that we had earlier, just for the children who are here who have not seen this before, to just take a look. These are the earlier programs that we had. And Honorable Chief Minister, Dr. Sawant, was with us all the while. These are the venues at NIO, the other venues that we had here. This was, in fact, I think this was last year, not the year 2020, when we had a scientist from Poland who came to speak to you. Today, incidentally, the areas that we are going to cover are space research, India's nuclear energy mission, technologies and machine learning, environment, disposal of plastic waste, sustainable development, energy storage, asteroids to worry about, forest ecosystems, Earth's biosphere, and nanobiotechnology. There's a wide variety of lectures. I hope you all make the best use of this. Today we are also conferring the Manohar Parrikar Yuva Scientist Award on Dr. Sai Gautam Gopal Krishnan. The chairman of the selection committee, Dr. Kakodkar, will give a brief on the selection process a little bit later. This science festival has attracted more than 30,000 students over the last 6 years. And in this 7th edition, we have about 5,000 students who will be attending across the state of Goa. I wish to place on record our sincere appreciation to Dr. Pramod Sawant, Honorable Chief Minister, who has always been supportive of this program, both in person, financially, and administratively. Also, our Honorable Minister for Science and Technology, Shri Montserrat, who couldn't make it here today. I extend a warm welcome to all of you, especially the student community. Please take advantage of these sessions. They are also available online. And as I end my talk now, There'll be a small movie that will be shown to you on Mr. Manohar Parrikar, Yuva Scientist Awardee, as well as the lecture series. Thank you.
Science today is transforming the way the world learns, works and progresses. Rapid advances in research, technology and innovation are reshaping industries, strengthening economies and improving the quality of life for millions. This wave of progress has also created new opportunities in education, inspiring young minds to explore, experiment and excel. Padma Bhushan Dr. Manohar Parrikar was a visionary who believed in building a Goa where scientific temper guided governance and education. An alumni of IIT Bombay, he led key policy reforms in e-governance, education and sustainable development that later became defining pillars of Goa's development model. Against this dynamic backdrop, the Manohar Parrikar Vidnyan Mahotsav MPVM has played a catalytic role in strengthening science education and expanding access to modern scientific knowledge in Goa. Over its past editions, the Mahotsav has consistently brought global expertise to local learners, enriching the academic ecosystem in meaningful ways.
I'm Mavila Sequeira, studying DY-BSc Botany in DCT's Temple College of Arts and Science. I've attended Manohar Parrikar Vidnyan Mahotsav last year, and it was a very interactive and innovative session. Science and technology shape every aspect of our lives today, and at the Mahotsav, we are seeing what are the latest development in science that will shape the future. Learning and interacting with people who are at the cutting edge of technology is a great experience.
Since its inception in 2018 as the Nobel Prize series, the Mahotsav has been guided by some of the most distinguished minds in science. Nobel laureates, national scientific advisors, and leading researchers from institutions such as ISRO, DRDO, IISc, Google, and renowned scientists from across the globe have addressed the students and scholars, sharing insights that inspire the next generation of thinkers and innovators. The impact of the Mahotsav on students and teachers has been far-reaching. To date, more than 30,000 students and members of the teaching community have benefited from its lectures, demonstrations and interactive sessions, making it one of Goa's most influential platforms for scientific learning.
My name is Tanay Anil Soiru. I am a student of biotechnology. I have attended Manohar Parrikar Vidnyan Mahotsav quite a few times. It has been a wonderful and enriching experience. Science and technology have shaped our future, and here at Mahotsav, we are able to learn, see the latest technologies advancement in the science field.
Now in its 7th edition, the Manohar Parrikar Vidnyan Mahotsav continues to grow in scale and relevance. In its 6th edition, the Mahotsav deepened its grassroots presence, evolving from high-profile keynote lectures to a multi-venue program that reached even the state's remote regions. This expansion marked a significant milestone in its evolution into a truly statewide science initiative.
It's important that while we pursue career in science or not is left to you, but you must remain engaged with science. So I think it's important to recognize that.
Thank you very much, Sir Norona, for these warm words and setting the tone for the day. Chairman, Manohar Parrikar Vidnyan Mahotsav Advisory Committee and former Chairman, Goa Public Service Commission. To begin this meaningful program, I request our respected dignitaries to kindly proceed for lighting of ceremonial lamp, symbolizing knowledge, wisdom, and enlightenment. May I request Director, Science and Technology, Shri Harish Konkar sir, to escort all the dignitaries on the dais. Requesting dignitaries to light the ceremonial lamp with prayers that may this lamp light the path of scientific thinking and innovation among our future generations.
Shubham kurutvam kalyanam arogyam dhanasampadah shatru buddhi vinashaya deepajyotir namostute deepajyotir namostute deepajyotir parabrahma deepajyotir janardanah deepajyotir parabrahma deepajyotir janardanah deepo hartu me papam sandhya deepa namostute o deepa brahma rupasvam jyotisham prabhuravyayah o deepa brahma rupasvam jyotisham prabhuravyayah arogyam dehi putrausha matim swachham hi me sada raverastam samarabhya yavat suryodayo bhavet raverastam samarabhya yavat suryodayo bhavet yasya tishte gruhe deepa tasya nasti daridrata shubham kurutvam
Thank you so much.
kalyanam arogyam
Kindly be seated. Late Sri Manohar Parrikar ji always emphasized innovation, research, and rational thinking. From classrooms to governance, his approach was deeply rooted in logic, simplicity, and scientific clarity. In Indian tradition, a floral welcome symbolizes respect, warmth, and heartfelt gratitude. We extend a floral welcome to all the dignitaries, a small gesture to express our deep appreciation and honor. May I request Harish Adkonkar sir to welcome all the dignitaries on the dais. Honorable Chief Minister Dr. Pramod G. Sawant. Warm welcome, sir. Chairman Advisory Committee and former Chairman Goa Public Service Commission, Shri Jose Manuel Noronha sir. Dr. Sunil Singh, Director, National Institute of Oceanography. Shri Pravimal Abhishek, IAS, Secretary, Science and Technology and Waste Management. Dr. Kiran Kumar, former Chairman, ISRO. Warm welcome, sir, to this festival. And Dr. Anil Kakodkar, former Chairman, Atomic Energy Commission. Thank you, Hari sir. May I now request Secretary, Science and Technology and Waste Management, Shri Pravimal Abhishek, to deliver his address.
Good morning to all present here. It is my privilege to address this August gathering at the 7th edition of Manohar Parrikar Vidnyan Mahotsav, a platform that has over the years evolved into a very vibrant confluence of ideas, inquiry, and inspiration. I warmly acknowledge the presence of our Honorable Chief Minister, Dr. Pramod Sawant, eminent scientists and visionaries, such as Dr. Anil Kakodkar. Sir, I'm truly inspired and very glad to meet you on this occasion. And Dr. Kiran Kumar, respected members of the advisory committee led by Shri Jose Manuel Noronha, Dr. Sunil Kumar Singh, and all the distinguished scientists, educators, researchers, and young participants joining us both physically as well as virtually in different locations in the state of Goa. This Mahotsav is much more than just an annual event, but it is also a living tribute to late Sri Manohar Parrikar, a leader who firmly believed that scientific temper is the backbone of good governance and national progress. May I also remind all the young minds here that the Constitution of India also prescribes cultivating scientific temper as a fundamental duty of every single person. Therefore, dear students, in this rapidly transforming world, science and technology should no longer be restricted to laboratories, but they should be brought out to shape how we manage our world, address pressing issues such as healthcare, climate change, education, and poverty. As the Department of Science and Technology and Waste Management, we view innovation as a powerful enabler for sustainable development, particularly in areas such as environmental protection, waste management, clean technologies, and circular economy solutions. Events like this, Mahotsav, play a crucial role in bridging the gap between knowledge and application. They provide young minds an opportunity to interact with stalwarts, ask questions, challenge assumptions, and dream fearlessly. Such exposure is essential if we wish to nurture future scientists, innovators, and problem solvers who can address real-world challenges with creativity and responsibility. The government of Goa remains committed to creating an ecosystem that supports research, encourages innovation, and promotes scientific thinking at every level, from schools and colleges to research institutions and startups. Our vision is to make Goa not only a beautiful state, but also a knowledge-driven state and an innovation-led state. I urge the students and young participants to make the most of this Mahotsav, listen closely, engage actively, and let curiosity be your guide. Science begins with asking the right questions, and platforms like this will empower you to do that. Before I conclude, I want to congratulate Dr. Sai Gautam, who is the Manohar Parrikar Young Scientist Awardee for this year. And I'm extremely pleased to realize just now that we both were from the same college. In fact, we both lived in the same hostel, and he is just 1 year junior to me at IIT Madras. So it's an extremely pleasant feeling to see my own college mate, hostel mate, to be on this dais receiving this awardee, and I'm so proud of you, and I'm sure that the entire alma mater is proud of you. And I extend my sincere gratitude to all speakers, organizers, institutions, and partners who have contributed to making this event possible. Thank you, and I wish you all an enriching and inspiring Mahotsav. Thank you.
Thank you, sir, for this wonderful address. As we all know, this Vidnyan Mahotsav reflects Parrikar ji's vision to ignite curiosity, to encourage questioning, and to inspire young minds to think beyond textbooks. We are proud to have amongst us, son of the soil, former chairman, Atomic Energy Commission, Gomant Vibhushan, Dr. Anil Kakodkarji. May I request him, sir, to deliver his inspiring address. Dr. Anil Kakodkar.
Honorable Chief Minister of Goa, Dr. Pramod Sawant, Chairman Advisory Committee that has been organizing these Vidnyan Mahotsav, Shri Jose Manuel Narona, my dear friend, former Chairman of ISRO, Dr. Kiran Kumar, Director of the institute where we are meeting, National Institute of Oceanography, Dr. Sunil Singh, Shri Abhishek, Secretary, Department of Science and Technology, Goa, and Dr. Atkonkar, Dr. Sai Gautam Gopalakrishnan, whom we are decorating with the Manohar Parrikar Yuva Scientist Award, distinguished invitees to this program, not only here, but in all other venues throughout Goa. Dear students who are assembled here in large numbers to be a part of this Vidnyan Mahotsav, ladies and gentlemen. We are all here to remember, respect and celebrate Shri Manohar Parrikar, a very distinguished son of soil, very distinguished chief minister and a very distinguished central minister who has made very many very significant contributions, particularly in the domain of defense. Actually, I remember long time back when I met him, and he was here as chief minister, and he described in just few sentences the mission. He says Goa is number one, and that of course is true if you open among, in terms of all parameters. Goa is very high compared to any other state in the country. And then he says Goa is small. I know almost every segment, every activity that's going on in Goa. And of course, he has his own background as an IIT and technocrat. So he had everything on his fingertips. And so his vision, he was very eager to put that vision into practice. Clearly, science and young people, these two, as I see it, were the key pillars of that vision. Think about this. We say India's economy is growing. And, engineers who are used to do root cause analysis, there are several factors. But then you go deeper and say, this depends on that. So what is the root cause? What is the fundamental driver? And you will find it is the young people. What is the fundamental thing that empowers young people? Today we are in knowledge era, and the key factor is knowledge, new knowledge. And within that, if you go even deeper, it is the knowledge about science, because that's what allows you to do new things. That's what allows you to do new technologies. That's what makes a country different, better, bigger, more impactful than any other country. And so this Vidnyan Mahotsav, which has been happening in Goa we are in the 7th edition now, is a very important feature of Goa's development and Goa's future, in my view. Because it inspires young people, into doing science, and it inspires young people to moving forward in science. In so doing, you have a connect between the young and not so young, and also between the young and the old. And this Mahotsav is a kind of networking, interaction and inspiration among all of them. And it's not that only old people inspire young. I must tell you, even young people inspire old. So it's a kind of a mutual event with a lot of synergy. I must thank Government of Goa for this opportunity to be the chairman of the selection committee for identifying the awardees the Manohar Parrikar Young Scientist Awardee, which is an important element of this Mahotsav, which was introduced thanks to vision of Dr. Pramod Sawant. And I must say, this again is a very distinctive feature, both among the states and also nationally. And it's in one way it's a competition. We try to identify the best. And in another way, it's an inspiration, because the awardees are here, even other, not just the awardee, but some of those who have been very close, they are also here in this festival. And they are also going to talk to all of you. So, I was mentioning yesterday one of the Nobel laureates, David Govt, once in a conversation he was telling that he was invited, he comes to India quite often, so he used to come. So, and then one of the features of his visit to India would be to talk to students. So, conversation in that context, he says, yes, you call a Nobel laureate, people get inspired, young people get inspired. But that inspiration is there for a while and it evaporates. Because there is a huge gap between young students and a Nobel laureate. But if you organize lectures by somebody who is, let us say, doing a PhD or just finished PhD, and his or her talking to young students, many of you would recognize that, oh, he or she is of the same age as my younger or older brother or sister. So, if he can do, I can also achieve the same thing. And that inspiration value is much more impacting. That inspiration is much more value. This is what he said. And I feel that's very true. And this is exactly what is attempted to be achieved as a part of this Mahotsav. A few words about the selection process. The process is, of course, it's an all-India process. We publicize the scheme very widely. You get nominations from across the country and also from abroad. But the condition is we want somebody who has decided that he or she would continue research work in India. And then, of course, there is a process of shortlisting on the basis of their track record, the nominee's track record. The shortlisted individuals, we actually talk to them and talk to them extensively. So depending on the number, it's a process that goes on for, I think most often it has been gone on for 2 days. And you would find that these are individuals who have not only made significant forays into advancement of science and technology, but also have created actual impact which has made the difference. Difference to advancement of science, difference to in terms of new technology, difference in terms of application of that technology. I will close by just pointing out that when we talk about doing good science, in my view, there are three things that we need to keep in mind. Number one, there has to be very high excellence. So when we do science, it should be comparable to best anywhere in the world. It should be impact making at that level, and it should lead to new things which others have not done till that time, both in new knowledge as well as new technologies. And that is what makes a country great. The second aspect, which is also equally important in my view, is that we should be able to understand the core problems in front of our country, India. And we should be able to resolve them through application of science and technology. So there is this India-specific, India's development-oriented contribution of science and technology, because that is what will propel our country faster. And the third, we should also recognize that while India is advancing, or for that matter, it is true with all countries, as countries advance, as countries' economic progress moves forward, so does the disparity. And disparity is an element which causes instability over a period of time. So we must have development models of progress in a manner where as a whole the country advances, economy goes forward, but we don't allow disparity to increase. Disparity has to be kept in check. So you need applications where you create a bridge that eliminates the divide between the haves and have-nots, between the rich and poor, between people who can access and people who have difficulty in accessing knowledge, facilities, whatever. And one good way, in my view, of doing that is to pay attention to our villages. You do things in villages, and in a knowledge era, you always say you work from office or work from home, it's the same thing. So according to me, you work in a city or work in a village, it's the same thing, and you can achieve as good a work, as good a contribution to development, as good a contribution to economy by working in villages. And I don't have to tell you, but Sridhar Vembu, the chief of Zoho Corporation, who moved his headquarters, global headquarters, from United States to Tenkasi in Tamil Nadu, is a great example of ability to do that. And that, in my view, is a great way of minimizing the disparity, which is equally important. So these are the three, directions in which we should focus science and technology and its applications. So in the end, let me use this occasion to congratulate Dr. Sai Gautam Gopalakrishnan, whom we are going to recognize shortly, and wish all of you, all young students present in this hall and also in other venues, all the best in your future careers. Again, whether you decide to move in the area of science or in any other areas that is more interesting to you according to your aptitude. But as that film just said, I think today the current era is something that science has to be a part of your life. Whatever you are doing, whether you are doing fintech, whether you are doing social service, whether you are doing sports, there is science everywhere. So make science a part of your life and think about how to leverage that to take the country forward. I wish all of you all the best in that effort. Thank you very much.
Thank you so much, Dr. Kakodkar, for these inspiring words. It is truly said that science progresses not only because of great institutions, but because of young minds that dare to think differently. Today, Government of Goa is proud to recognize such brilliance through Manohar Parrikar Young Scientist Award, an honor that celebrates curiosity, creativity, and commitment to innovation. May we please give a huge round of applause to Dr. Sai Gautam Gopalakrishnan. And as I invite the awardee on stage, can we have chair for Dr. Sai, please? Doctor, please come on stage. Let's remember that we are not just giving a trophy or a certificate, we are recognizing a spark that has potential to light many lamps of knowledge. Dr. Sai, please take seat. Dr. Sai Gautam Gopalakrishnan is an early tenured associate professor of materials engineering at the Indian Institute of Science, Bengaluru, where he leads a research group in computational materials science and materials informatics. He has made seminal contributions in discovery, design, and optimization of materials. Dual degree BTech and MTech in metallurgical and materials engineering at IIT Madras. PhD in materials science and engineering at Massachusetts Institute of Technology. He joined Indian Institute of Science as an assistant professor in 2020. He's been recognized as Young Engineer, Young Associate, Academy by National Academy of Engineering, Rising Star by American Chemical Society, Early Career Scholar by Materials Research Society, Emerging Investigator by Royal Society of Chemistry, Young Metallurgist by Ministry of Steel, Government of India, Young Battery Researcher by IMESD, recipient of Professor Preeti Shankar Teaching Award. Department of Science, Technology and Waste Management, Government of Goa is pleased to confer on him the Manohar Parrikar Yuva Scientist Award for 2025. Congratulations, Dr. Sai, on behalf of all the people from Goa. Thank you so much. Requesting dignitaries to please take seats. Dr. Sai, please take seat in the auditorium. And may I now request Dr. Sunil Singh, Director, CSIR NIO, to deliver his address.
Good morning, everybody. Honorable Chief Minister of Goa, Dr. Pramod Sawantji, eminent keynote speakers, Dr. Anil Kakodkar ji, Dr. S. Kiran Kumar ji, Dr. Sai Gautam Gopalakrishna, awardee of Manohar Parrikar Young Scientist Award 2025, Chairman of the Manohar Parrikar Vidnyan Mahotsav, Sri Jose Manuel Narona ji, Distinguished Secretary of Science and Technology and Waste Management, Sri Abhishek ji, the Director, Sri Harish ji, respected scientists, technocrats, faculty members, dear students, ladies and gentlemen. It is my distinct honor and privilege to welcome you all to the 7th edition of Manohar Parrikar Vidnyan Mahotsav. The annual festival is a heartfelt tribute to the birth centenary and lasting legacy of Sri Manohar Parrikar ji, a visionary leader, an IT graduate, and a true scientific mind. I remember India was celebrating the Nobel laureate meet in 2016, the first meet. And it was decided to have this Nobel laureate meet in every year in different part of the country. And the second Nobel laureate meet was organized at Goa. And that time, Chief Minister Parrikar ji was there. And in that meeting, he announced that why 1 year? We are going to have every year the Nobel laureate meet. And unfortunately, after that, actually, his demise created a great vacuum. But then everybody in Goa government agreed to start this annual meet. So since then, 2019, you have seen every year we are having this meet. In many of the scientists from India or abroad or Nobel laureate, they are participating and delivering lecture, instigating the new minds, young minds for doing the science. In form of a festival, because you know whenever we are doing some festival, it connects to the people, and that's why this festival, event has been named as a festival. When we are talking about Viksit Bharat, developed India, or Atmanirbhar Bharat by the 2047, see, when we are talking about 35 trillion economy, it will not just be attained just by acquiring the wealth. We have to have the knowledge creation. And knowledge creation can only happen when young minds are involved with the doing science, doing the research, and all those things. We need a knowledge-based economy. We need a knowledge-based development. And for that, actually, this type of meeting is very, very important. Today, if you see in country, higher education, today almost more than 4 crore people are enrolled. Out of that, at PG degree level, about 55 lakh people are there. Only 8 lakh people are doing science in post-graduation. Out of that, only 42,000 people are getting registered. The students are getting registered for PhD. And at the end of the PhD degree, only 10,000, roughly 10,000 people are getting PhD degree. A country with 1.4 million people, the knowledge creation where it is happening, the PhD degree, we are only having 10,000 PhD every year. If you compare the same thing with the US, they are having 4 times higher with 1/4 of the population. So you can imagine how we are lagging behind. Just this is to give you the impression how we are doing. I'm not saying we are doing bad. We are doing quite well. If you see the number of publications, 3 lakh it is touching per year. We are ranking number 3 in the world after China and US. But the disparity is very long. You see that China is publishing 10 lakhs, US is publishing 7 lakhs. We are roughly 2.8, 2.9 lakhs. Not only that, when you are talking about numbers, the quality, I think comparison is very, very difficult. So still, I think when you are talking about knowledge creation in terms of publication and all, we are doing good. But when you are talking about the conversion of this knowledge to the technology, to the innovations, we are not doing at all good. And when we are thinking of Atmanirbhar Bharat, self-reliant India, I think it is very much required to have both the knowledge creation and technology development. And I think our young minds have to play a big role. And I think this type of festival has to organize, and anyway it is being, but at different locations, many places, which will keep this state, not only this state, but the entire country will take in very different the level. So for that purpose, I think I'm very happy that this is continuing. We are very much happy that we are part of that. So thank you very much at this participating in this festival. I'm very happy that a lot of people are getting enthusiastic participation. So at the end, I think I wish you all a very happy listening of the different lectures. Thank you very much. Thanks a lot.
Thank you very much, sir. As a chief guest of today's function, we have with us Honorable Chief Minister of Goa, Dr. Pramod Ji Sawant. A true disciple, a humble disciple of late Sri Manohar Parrikar Ji, walking on his footsteps and adding his own vision, his own spirit, his innovation, and his creativity. The dreams which he has seen for Goa, the development which he has planned for Goa, and aspirations that he has for every Goan, be it a child, a youth, or a senior citizen. As he often says, development should reach till the last person, and striving to achieve that dream day in and day out. We are pleased to have with us dynamic, dashing, dedicated, and disciplined Chief Minister, Dr. Pramodji Sawant. Kindly guide us on this very special occasion with your inspiring thoughts. Dr. Pramodji Sawant.
For the 7th Manohar Parrikar Vidnyan Mahotsav 2025, amongst us the former chairman of the Atomic Energy Commission of India, Dr. Anil Kakodkar, Dr. Kiran Kumar, the former chairman of the ISRO, chairman of Advisory Committee of the Manohar Parrikar Vidnyan Mahotsav, Sri Jose Manuel Narona, Secretary for the Science and Technology Waste Management, Sri Parimal Abhishek, Director CSIR National Institute of Oceanography, Sunil Singh, and the awardee of the Manohar Parrikar Vidnyan Mahotsav, Dr. Sai Gautam Gopal Krishnan. Eminent scientists and distinguished speakers, they engaging with the students across the state today. म्हणजे समेस्त गोंयकार आनी गोंयच्या साबार तरणाट्यांक येवकार. आमी पळयता की गोंय हें अशें राज्य आसतलें ज्या जाग्याचेर 19 सायंटिस्ट 18 जाग्याचेर एट अ टायम एकाच दिसा इतक्या मोठ्या प्रमाणात आमी मनोहर पर्रीकर विज्ञान महोत्सव सेलिब्रेट करता. ही संद तुमकां बाकी खंयच्याच राज्यांत अशा पद्दतीत पळोवपाक मेळची ना. म्हाका सांगता आसतनाय बी खूब खोस भोगता मनोहर पर्रीकर हांच्या यादीत सुरू केल्लो हो मनोहर पर्रीकर विज्ञान महोत्सव गोंय राज्या खातीर तितकोच खाशेलो आसा. आनी म्हाका दिसता गोंयच्या प्रत्येक तरणाट्यान हाचो फायदो घेवचो. आनी म्हणून तर हांव दर ह्या कार्यक्रमाक फाटलीं 7 वर्सां न चुकता हांवूय प्रेजेंट रावता आनी गोंयच्या म्हज्या साबार तरणाट्याक सांगता की मुद्दामून आमी सगळ्या जाणांनी हो कार्यक्रम पळोवचो. हाच्याच बरोबर म्हाका सांगता आसतना खूब खोस भोगता डॉक्टर अनिल काकोडकर हांच्या बरोबर हांव आतांच डिस्कशन्स करतालो. गोंय हें एकमेव राज्य अशें राज्य आसा ह्या बारकुल्या राज्यांत आमी जर पळोवंक वचत जाल्यार आमच्या खातीर सायंटिफीक नॉलेज दिवपी इतक्या मोठ्या प्रमाणाची इन्स्टिट्यूशन्स हांगासर एवेलेबल आसात. घडये कदाचित तुमी बरीचशी इन्स्टिट्यूशन्स आजून पळोवंकूय ना आसतली. पोलार इन्स्टिट्यूट सायन्स एट वास्को, द नॅशनल इन्स्टिट्यूट ऑफ द ओशनोग्राफी ज्या इन्स्टिट्यूशनांत आमी आज बसल्या, ICR एट ओल्ड गोवा, आयुष इन्स्टिट्यूट एट धारगळ, एट नॅशनल फॉरेन्सीक सायन्स एट प्रेजेंट एट कुट्टी, IIT कॅम्पस एट फार्माकुडी, NIT कॅम्पस एट कुंकलीम, National Water Sports Institute in Donapaul, GIM Institute in Sakli, BITS Pilani at Verna, हाज्या भायर नवीन इन्स्टिट्यूट सुरू जावपी MIT Institute in Thivi and Parul Institute in the Kepe and Ganpat University which is establishing for the coming years for the marine science. इतक्यो सगळ्यो इन्स्टिट्यूट गोंया सारकेल्या ह्या धाकल्याशा राज्यांत आमी हाचो बेनिफिट्स म्हाका दिसता आमी सगळ्यांनी घेवपाक जाय. आमचे फ्युचरिस्टीक जे सायंटिस्ट जावपाचे आसा तांच्यांनी घेवपाक जाय. म्हणून तर अशा पद्दतीचे इन्फ्रास्ट्रक्चर, अशा पद्दतीच्यो डिफरंट इन्स्टिट्यूट्स म्हणजे थँक्स फॉर द गव्हर्मेंट ऑफ इंडिया, थँक्स फॉर द हॉनरेबल प्रायम मिनिस्टर नरेंद्र मोदीजी ज्यांच्या ह्या कार्यकाळात आमी ह्यो उरलेल्यो 4-5 इन्स्टिट्यूट्स हांगासर एस्टाब्लीश करपाक शकले. हॉनरेबल प्रायम मिनिस्टर्स विजन इज ऑलवेज अबाउट द विकसीत भारत 2047 हे साकार करता आसतना ते सातत्यात इनोव्हेशन, टॅक्नॉलॉजी, रिसर्च ह्या सॅक्टराचेर सातत्यात उलयता. आनी म्हणून तर तांच्यांनी सुरू केल्लो माय भारत हो पोर्टल, माय भारत ह्या पोर्टलाचेर जर तुमी वचून पळयशात जाल्यार म्हाका दिसता की डिफरंट ऑपॉर्च्युनिटीज वीच इज एवेलेबल फॉर द यंग मायंड्स आनी तांच्या खातीर ह्यो ऑपॉर्च्युनिटीज तुमी सगळ्या जाणांनी ग्रॅब करच्यो अश्यो म्हाका दिसता. हाच्या खासा सुवाळ्याचेर उलोवपा खातीर हांव मुद्दामून द सायन्स टुडे शेप्स ऑलमोस्ट द एवरी पार्ट ऑफ अवर लायफ्स, फ्रॉम हाव वी अंडरस्टँड नेचर टू हाव वी डिझायन सोल्युशन फॉर सोसायटी. The platforms like Manohar Parrikar Vidnyan Mahotsav reminds us that the science not limited to textbook or laboratories. It begins with a curiosity and grows through questioning. Goa has contributed meaningful to India's scientific journey. We recall with the pride Gomanta Bhushan who's amongst us Dr. Anil Kakodkar, whose leadership strengthened the India's capability in the strategic and energy-related technology. He's also remember Dr. Raghunath Ananta Mashilkar, whose work connected the research and industry and the public purpose. Dr. Damodar Dharmananda Kosambi, and whose analytical approach reshaped thinking across the disciplines. The journey shows how scientific thinking can influence the society, far beyond the academic boundaries. To encourage the research and original thinkings amongst the young scientists, the Manohar Parrikar Yuva Scientist Award, carrying the cash prize of ₹5 lakhs, has been instituted. This award has been effective to value innovations and scientific excellence and to motivate the young researcher to pursue the rigorous and meaningful work. This year, we are honored to have the Dr. Sai Gautam Gopal Krishnan, the Associate Professor of the Indian Institute of the Science, Bengaluru, as the recipient of the Manohar Parrikar Vidnyan Award 2025. Once again, congratulations to you. His work in the material science represents the focused research with real-world relevance. The scale of this year's Manohar Parrikar Mahotsav is encouraging. The 19 prominent scientists and engaging with the students across the 18 venues throughout Goa, and 4,500 students are participating, interacting with the ideas across the fundamental science, engineering, the life science, environmental studies, data science, artificial intelligence, health science, and emerging the interdisciplinary areas. One of the most valuable aspects of the Mahotsav is direct interactions. When the students listen to the scientists speak about their journey, the challenges faced, the experiment attempted, and the lesson learned since becoming the relatable. Such conversations often spark new interest and help the students to see the research as an evolving the pursuits rather than fixed destinations. To the students present here today, I would like to say that the science move forward because of the some choose to ask the more questions. Do not hesitate to explore to face the uncertainty. The every efforts contributes to learning. The teachers and mentors, they play an important role in shaping the journey. By encouraging the critical thinking and experimentations, the educators helps the transforming the curiosity into capability. I extend my appreciation to all the teachers and who continue to guide the students towards the thoughtful and responsible inquiry. I also commend the Department of the Science and Technology and the Waste Management, and along with all the partners of the institutions for organizing this Mahotsav across the multiple venues and dedications of careful coordinations. Such initiatives will help us to ensure the scientific learning remaining accessible and engaging. As the Manohar Parrikar Vidnyan Mahotsav continues to grow to bring the forth an important idea that science belongs to everyone. When the knowledge is shared openly, discussed freely, it shapes to important citizen. I hope this 7th edition ignites the curiosity, encouraging the learning and inspire the students to pursue the experience in the chosen field. I wish this Mahotsav every success and adopts to leave the listened impressions for all who participates. Once again, my best wishes for all of you. Thank you, one and all.
Thank you so much, sir, for these words of inspiration, enlightenment, and motivation. Thank you so much. May I request Sir Narona to present mementos to all the dignitaries on the days as a mark of respect and gratitude. Honorable Chief Minister, Dr. Pramod Sawantji. So thank you so much for gracing the occasion. Dr. Anil Kakodkar. Dr. Kiran Kumar. Shri Pravimal Abhishek. Dr. Sunil Singh. Shri Harish Adkonkar. For all the hard work. Thank you so much. And may I request Honorable Chief Minister to present memento to Sir Jose Manuel Noronha. We sincerely appreciate your tireless efforts, meticulous planning, and unwavering commitment. Thank you so much, sir. I now request Director, Science and Technology and Waste Management, Shri Harish Adkonkar, to propose words of thanks.
Good morning, all. On the occasion of 7th edition of Manohar Parrikar Vidnyan Mahotsav 2025, I would like to thank Dr. Pramod Sawant, Honorable Chief Minister of Goa, Dr. Anil Kakodkar, former Chairman, Atomic Energy Commission of India, Shri Jose Manuel Noronha, former Chairman, Goa Public Service Commission and Chairman, Advisory Committee, Dr. Kiran Kumar, former Chairman, ISRO, Dr. Sunil Singh, Director, National Institute of Oceanography, for being the host of this function, our Secretary, Shri Parimal Abhishek, IAS, Secretary, Science and Technology and Waste Management, for his support, all the speakers at all at various venues, the team GWMC and Department of Science and Technology and Waste Management, all our advisory boards, technical partners, supporting partners, all educational institutions who have been kind enough to ensure that the students are present for this Mahotsav, all the students who are present here today and who have been connected through YouTube and Facebook, press, the digital media, and each and everyone present for this function. A warm thank you to you all. Thank you.
Thank you, Harish sir. Here we end our inaugural session. It is really good that we started right on time and we ended the inaugural session right on time, see 10:30. Thank you so much. I request all the dignitaries to take your seats in the auditorium for next technical session. Thank you, sir. There will be 3 sessions, and may I request Shri Sujit Dongre sir, Scientist, Center for Environment and Education, to kindly take over the further proceedings.
I think we are now getting into our technical sessions. I'm extremely happy that we are on the 7th edition of Manohar Parrikar Vidnyan Mahotsav, which was started as a concept. Now it has grown into a full-fledged Vidnyan Mahotsav, which is a flagship program of the Department of Science, Technology and Waste Management. And I'm very happy that a student wait for this day, wherein they'll get an opportunity to meet eminent scientists of global stature. So the first lecture is a keynote speaker who is none other than very known eminent scientist who has worked with a very important institution called ISRO. I'm very, very happy to introduce Dr. A.S. Kiran Kumar. Dr. A.S. Kiran Kumar is a Vikram Sarabhi professor at ISRO Bangalore and member of the Space Commission, Government of India. He is also a member, Governing Council, Indian Institute of Science, Bangalore. During 2015 to 2018, he has served as a Secretary, Department of Space and Chairman, Indian Space Research Organization. Dr. Kumar has steered the implementation of the application-oriented Indian space program in India, which has facilitated rapid development of the country in many important spheres of Earth observation, communication, navigation, meteorology, and space sciences, as well as the development of indigenous launch vehicle and related technologies for providing assured access to the space. He has led and designed and development of more than 50 electro-optical imaging sensors flown on various space-borne platforms starting from Bhaskara in 1979. Further, his role in the success of Chandrayaan-1 mission and Mars Orbiter mission has been very significant. We are very happy, and I request all of you to welcome Dr. A.S. Kiran Kumar with applause. May I request Dr. Kiran Kumar, sir, please take over the session. Okay. Yeah, okay.
Good morning to all of you. Good morning. Yeah, thank you. So thank you very much for this opportunity to be amongst you on this very important occasion where State of Goa is remembering a great son of the soil who has made very significant impact in the lives of not only Goa but also the entire country. And it's a great privilege to deliver a talk in his memory. What I intend to do is take you through the journey of India's space program and through that link to the many of the aspects which both Anil Kakodkar and Pramod Sawantji addressed in what we need to do for the future. So probably you're all very familiar. The humanity got a very new capability, a sort of disruptive technological capability of putting an object in space. This happened because two superpowers after the World War were trying to enhance their own capability, and with intense competition, they were moving ahead. Russia put the first object in space, Sputnik, in the year 1957. And you also remember, we got independence in 1947 after many centuries of external rule. So obviously, if you look at 1957, it was just 10 years into independence, and India was struggling to provide food, shelter, and education to its citizens. At that time, we had a great visionary scientist, Dr. Vikram Sarabhai, who was looking at how this disruptive technological capability of going beyond planet Earth can make a difference to the lives of people in the country. So what I intend to take you through is that journey where Dr. Sarabhai visualized how space technology can help the country. See, he said at that point of time, we should be second to none in the application of advanced technologies to the real problems of man and society. And Professor Satish Dhawan, who actually followed him, was also the person whom we consider as the person who built the culture in the organization. He said, to assure its development, India views science and space technology as a crucial apparatus for its socio-economic development. And if you look at India itself, some of the basic facts are, we are only 2% of the world's geographical area, 4% of the world's water resources, 17% of world's population, and population by 2075, of course, 1.6 billion. We have socio-cultural diversity, connectivity over and diverse terrains. Adult literacy is very low. These were, of course, at some earlier point in time which was made. So with this, productivity and then predominantly rain-fed agriculture, then you have got per capita availability of land is very limited, and then very low irrigation efficiency. These were many of the problems that was facing the country. Then, like I said, 4th October 1957 is when humanity got its technological capability of going beyond Earth. And then, at that time, Dr. Sarabhai looked at how this technology can help the country. Because he knew that if you put a satellite at a height of 36,000 kilometers, because of the relative velocity of satellite moving around the Earth, it takes 24 hours, and Earth itself rotates once in 24 hours. Because of the relative velocity becoming zero, the satellite looks at 1/3 of the globe in a continuous fashion. So he was looking at how can we make use of this capability. So he convinced his friends across America, Russia, and Germany, told them, in India we have a unique place which is a geomagnetic equator, and if at that place, if you conduct upper atmospheric research, it will be beneficial for the entire scientific community. With that in mind, he could get sounding rockets to be brought to India from America, and then it was actually first rocket was launched in Tumba. You see a dilapidated church in this image, and it was in that church the first rocket got assembled. And for launching this, of course, one of the things that was required was convincing the fishermen that we need to make use of this place. I'll touch upon that little later. What Dr. Sarabhai did was, India needed to develop ability to communicate to all its citizens. So for this, one of the things that was done is, he could convince Americans that when they were building one of the most advanced technology satellite called ATSF, and borrowed it and moved it over India. See, like I said, a satellite at geostationary orbit can look at 1/3 of the globe. And using that, you can actually do line of sight communication. India conducted the world's largest socio-technological experiment at that point of time. In 1975, borrowing this satellite from America. Today we are all familiar, a 1/4 meter antenna on our rooftop. With a set-top box, you can see television programs. You imagine in 1975, when only 4 metros had the privilege of seeing this television, Dr. Sarabhai could make use of the capability of this technology. And in 2,400 remote villages of our country, using a 10-foot diameter antenna and almost half a rack height of front-end electronics with black and white televisions built at ECIL, the experiment was conducted for 1 year, and it was demonstrated how information can be reached to remote places in the country. And also, obviously, you can see if in 1975 you go and tell the people who are running the country what you are speaking can be heard all over the country at the same time, you don't require too much of a convincing for new technology to be adopted. And then this particular experiment proved that India can make use of the space technology and move ahead. And again, 2 important aspects you need to remember in this is, Dr. Sarabhai was able to convince Americans one of the most advanced technology satellite they were building. It had a life of only 2 years. Out of the 2 years life, they were ready to provide it to us for 1 year, because as you can see, a geostationary satellite, if it is visible over America, in India we cannot see it. So if we want to use over India, that satellite had to be brought over the Indian longitude. That means a satellite which they were building had a life of 2 years, and out of that, they were ready to give it to us for 1 year. And that convincing was what was the ability of Dr. Sarabhai. And of course, they had other interests also, because at that point of time, direct to community television, what India demonstrated, become the actually predecessor for today's direct to home television. So this is actually the starting point for developing commercial applications for them. And then if you see, at that time, what we did was borrowed an American satellite. And this year we actually celebrated 50 years of Indian in the site experiment. On 30th of July this year, India launched a satellite called NISR. And if you see this,
synthetic aperture radar satellite. This groundbreaking low Earth orbit, LEO observatory, promises to revolutionize the way we understand our dynamic planet. Equipped with state-of-the-art L and S-band synthetic aperture radar, SAR systems, NISR will use the sweep SAR technique to deliver high-resolution images across vast swaths of the Earth's surface. Incredibly, it will map the entire globe every 12 days, offering unprecedented consistency in spatial and temporal data. NISR's mission is nothing short of transformative. From tracking glacial melt and monitoring agricultural landscapes to analyzing seismic shifts and managing disaster response, it will empower scientists, researchers, and policymakers with vital insights. By precisely measuring minuscule movements and colossal environmental events alike, NISR will help us decode Earth's complex ecosystems and natural hazards. This flagship mission sees NASA contributing the L-band SAR, engineering payloads, and critical systems like GPS receivers and the solid-state recorder. ISARO provides the S-band SAR spacecraft bus and its vehicle, GSLV F-16. NISR will be launched from the spaceport of India, SDSC Shar. A majestic 12-meter unfurlable reflector antenna will unite the dual-band systems, enabling powerful Earth observations from orbit. With an open data policy and the NISR utilization program, NISR-UP, encouraging Indian researchers to lead transformative studies, this mission symbolizes a leap towards sustainable living and informed disaster resilience. NISR is not just a satellite, it's a symbol of global unity, scientific excellence, and hope. It promises to safeguard our future by helping humanity live more wisely with nature.
Actually, you can see in this particular activity how India started its space program with the help of borrowing an American satellite and demonstrating how technology can be used for India's development to a point where India worked together with Americans and the most advanced technology satellite built ever. This satellite costs almost $1.5 billion, out of which India has spent only 10% of that, but then it's a one-to-one collaboration. We built the satellite launch vehicle, we have put it into orbit, and now over last 3 months, it has been made operational, and we are getting very useful data about the Earth. And then you can imagine if a human body is being monitored by pulse rate or various parameters 24/7, you can predict what kind of ailments that is going to be there. This particular satellite actually monitors Earth in all spheres of whether it is ice, water, solid Earth, or atmosphere, and then it generates more data than all the satellites put together till now. And this is a path-breaking satellite which is available to the humanity, and because of its resolution and because of its capability, it's a great service to the humanity. And what India has demonstrated over these 5 decades is from being a borrower of technology to a collaborator and then almost equal to others in the world. You will see some more examples subsequently. In fact, this is one activity where Dr. Sarabhai had to convince the fishermen in that place in Tumba for conducting our experiments. The fishermen had to allow us to do this activity. So for this, he had to use the services of Bernard Pereira and to convince the fishermen, you allow us to work on this place, one day the country will benefit. So what happened was, 1999 onwards, using the orbiting satellites, we were able to look at the color of the ocean in different wavelengths, and through that identify the chlorophyll, and from chlorophyll the food chain of the fish, and then tell the fishermen where in the ocean if you go, you will be able to catch the fish. You can see what was promised to them in 1970s became a reality 99 onwards, and in fact now we have gone one step further. A small battery operated gadget is fitted into the boat of the fisherman, making use of our navigation satellites and the messaging system. A mobile in the hands of the fisherman communicates with this gadget and shows him in a video compass mode where he has to go for fishing. And then it gives him alerts about if the sea state roughness is going to be unbearable or if wind and weather is going to be unbearable. It alerts him in his mother tongue. And also many times you have seen our neighboring countries capture fishermen because they are wading into their waters. So all this alert is happening in the mother tongue, in the mobile he is carrying. So this is an example of the most advanced technology of rocket and satellite application, enabling a person who does not know reading or writing. We have a 11,500 kilometer long coastline and lakhs of fishermen depending for their livelihood. So the space technology has enabled them, and today many state governments are providing such gadgets to the fishermen for doing their activity. And then another very important thing that happened using the space technology is cyclone prediction itself. In the earlier era, cyclones used to take away tens of thousands of lives before the impact was actually not known when the cyclone will come. But with an satellite, geostationary satellite, you can look at the cloud pattern and various parameters and predict well in advance where a cyclone is going to hit the coastline, and then disaster relief agencies are able to evacuate people and save their lives. While in the earlier decades, the loss of life used to be 10 to 15,000, today, in the recent past, you have seen the loss of life has reduced to single-digit numbers. In a similar manner, the previous activity which I was mentioning, the act of telling the fishermen where they can catch the fish saves to the country between 10 to 15,000 crores a year. Now, based on the satellites orbiting, you can do a whole lot of activities of Earth observation, satellite communication, broadcasting, tele-education and telemedicine, NAVIC application, disaster warning, and also strategic application. In all this, the satellite data can provide very useful information. Today, what India is doing is, based on a large number of observing instruments, It has got data over Earth, and then making use of a digital elevation model and navigation information. Using large number of models, it is able to provide necessary information for socio-economic security, sustainable development, governance, and many such activities. In fact, one of the things that the country has done is making use of the information extracted from the satellite-based sensors, a whole lot of activities of how to make use of it for various government activities and governance activities. What was done in 2015 was Honorable Prime Minister asked us to conduct an activity where all the state and central secretaries and various departments, they were brought together and they were told the advantages of using space technology information. In fact, on that day, Honorable Prime Minister himself spoke for 45 minutes extempore, telling the various ministries how space technology can be used for different applications. Over a period of time, this information extracted from space-based observation has been used by different departments, and departments have adopted this at their own pace. Forest Survey of India started using it way back in '87 to generate biennial maps. Then INCOIS, Indian National Center for Ocean Information System, started providing prospective fishing zone information from '99. Then Ministry of Agriculture started using this data for telling what crop is being grown, how much is the yield this year. Then Department of the Weather Monitoring, IMD, and also the Airport Authority of India, all of them started using this technology. India also started working with international agencies for building its capability, whether it is Megatropic, SARAL, or just now what I showed you, NISAR. And it also provided what is called as a South Asia satellite, where true to our tradition, the knowledge and skills you acquire should not only benefit you, but also benefit your neighbors. Honorable Prime Minister made sure that our ability to put transponders in space can help our neighboring countries make use of broadcasting, communication, and even weather information dissemination in the neighboring countries. And in this, I'm just reminded of one thing that happened on that day. When we launched this satellite, all the heads of the states of our neighboring countries were present on a video program, and the President of Afghanistan made a statement which he said, "We are used to people making promises, but I'm seeing a promise being fulfilled in a real quick time." And he complimented the Honorable Prime Minister for achieving what he had promised to SAARC. And then while we built the capability of building this space technology for various applications, India also made use of it for space science activity, and every opportunity was made use of. Like the sounding rockets, initially it was used for studying upper atmosphere by providing sodium vapor and how it gets distributed. Aryabhata, which was launched in 1975, our first satellite, carried some space science experiments, and progressively we made use of the satellite for different science activities, Chandrayaan, Mangalyaan, and then Aditya L1. We will see some of the details in subsequent slides. And India's maiden moon mission, if you see, this was done in the year 2008, and as you can visualize, man had landed on the moon way back in 1969, and a large number of probes had touched the surface of the moon. But still, when India did this experiment in Chandrayaan-1 in 2008, the credit it got is discovering the presence of water molecules and also the process of water molecule formation on moon. Credit of discovering that goes to Chandrayaan. So what it shows is, in the area of science and technology, it is never too late. You can always do something which others have not done. And this particular example showcased that India, though started its space program in a much later, but it was also able to make an impact in the global community. And similarly, if you look at Mars mission, in 2014, when the satellite went around the Mars, it was a great achievement because in a very first attempt, a country was able to put an object orbiting Mars. And if you were to appreciate the complexity of this mission, on 2013, November 5th, when this satellite was launched from Sriharikota, the task cut out for the satellite was travel a distance of almost 600 million kilometers over a period of 10 months. And at the end of that period and journey, you imagine in space a cube of 50 kilometers. This satellite had to be inside that cube on a specific time, that is on 2014, September 24, morning 7:30 a.m. On that second, if this satellite was not inside that cube, it would not have been possible for us to make the satellite orbit Mars. And what all could have deviated that satellite trajectory? Many of you are aware, sunlight falling on a surface produces a radiation pressure, and that force itself, satellite receiving sunlight, can deviate its trajectory over this 10 months period by hundreds of thousands of kilometers. So you not only should you make sure that your trajectory is correct at a specific time, it should be at a specific location. So all this complexity was successfully done. And another very important aspect is India was able to build this technological capability within the constraints of its launch vehicle. While others were doing moon and other program with very powerful rockets, we did it with a rocket which had limited capability. But then, in spite of that limitation, we were able to make use of the knowledge that every time satellite comes at perigee, if you can add a small energy to it, it will start moving further. Just to make the point clear, if you want any object to go around any planet, when it's at a specific height, you give a direction and a critical velocity, then it will go around that planet in a circular orbit. So if you give more than the critical velocity, then the point of release becomes perigee and the other side becomes farther apogee. So every time the satellite comes at perigee, you can add a small energy by operating the thrusters on that. Then you can move it, make it further. So since we had our launch vehicle with a limited capacity, we put the satellite in an elliptical orbit, and then over a period of time started making it go further and further. So that's how we did both moon mission and Mars mission. And with the limited technological prowess of satellite being launched by our launch vehicle, we could achieve this. And that's how in 2014, world looked around at India in amazement how it was possible for a country to achieve this. And also, every time you are doing something, you are converting your limitation into an advantage. In fact, this Mars mission generated more global images of Mars than any other satellite orbiting Mars. Then we also built a satellite called AstroSat, a satellite which is carrying a telescope looking at a specific wavelength region in the far ultraviolet region, and it has a sensitivity better than any other operating satellite today, even when comparison with Hubble or even James Webb. In this particular wavelength, this satellite provides information to our scientists better than any other observing satellite today in space. And here again, if you want to appreciate the basic concept, when you are looking at stars or systems from ground, atmosphere intervenes between you and the object, and because of the atmospheric effects, your seeing is limited. So even with a large telescope, when you see from ground, atmosphere can be limiting. But if you go beyond the atmosphere, you can get very good observation capability. That's how this AstroSat, which was again launched almost 10 years back, we celebrated 10 years of the performance of this. While its original life was only 5 years, it has lasted for more than 10 years, and it is continuing to provide very unique information, virgin information to our scientists, and a lot of scientific findings have already happened using this data. Then after Chandrayaan-1, in Chandrayaan-1, we had a moon impact probe which touched the surface of the moon in an uncontrolled manner. In Chandrayaan-2, our attempt was to land the lander in a controlled manner. But then we failed in our first attempt, and of course, based on the learning of what happened in Chandrayaan-2, we were able to successfully put Chandrayaan-3, and then you saw in August 2023, how India achieved landing Vikram lander and Pragyan rover on moon. And many of the findings of Chandrayaan, in fact, Chandrayaan-2 learning in the failure provided all the necessary inputs for us to succeed in Chandrayaan-3. And it is here that we need to really appreciate the basic situation. See, if you are trying to do some activity, and if you want to be 100% assured of success in that, you have to operate within the limits of your skill and knowledge. That means you are not pushing yourself beyond your current boundaries. Obviously, when you are doing that, nothing new emerges. If you want to do something beyond what others have done, or you want to move yourself ahead, you have to go beyond your current knowledge and skill. And if you do that, what is assured is failure, not success. If you succeed in first attempt, maybe it is sometime by chance. But that is where you should be prepared for failure, because when you are pushing yourself beyond your current knowledge and skill, you are taking risks. And these risks ensures that it is, success is not assured. But then if you can learn from the failures and then go ahead, you can make sure you can achieve great successes. So for example, what is it between Chandrayaan-2 and Chandrayaan-3 which helped us achieve the success? In Chandrayaan-2, for the first time, we were trying to build an engine which had what is called a throttling capability. Why was it required? Until that time, all the launches what we had done, whether geostationary or etc., were making use of engines which once started will deliver a fixed thrust till the fuel is there. That means it keeps on delivering a fixed output until the fuel is there. But when you want to land on a planetary body, as you keep coming down, you are compensating the gravity of that planetary body, and as you keep coming closer and closer to the surface, because of the mass reduction of the fuel being consumed, unless you are able to change your thrust value, you cannot do soft landing. That means you need what is called as a throttling capability. Like in your scooter or car, you have to press the accelerator or decelerate so to meet the requirements. So we were building for the first time an engine with such throttling capability. So in the very first attempt, obviously some limitations came, and also our resource constraints of how much fuel we could carry in the rocket when they determined our ability to perform. But in Chandrayaan-2, we had an imaging sensor which took very high resolution pictures. I'll just showcase to you probably what I wanted to tell. So this particular slide captures what was done in a descent. When you are orbiting a planet or a satellite like Earth satellite Moon, then you are moving at a velocity of something like 1.6 kilometer per second. If you want to touch down on the surface, your velocity has to come down to 0. If you kill the horizontal velocity, then you are almost like suspended. The pull of the moon's gravity keeps pulling it towards that. To compensate that, you operate the engine and then you can hover. So we traveled almost 700 kilometers before touchdown and gradually came to a point and touched down on the surface. So if you want to touch on a place, what is it that you need to know? You need to know about the terrain, because whether there are craters, whether small boulders are there, the 4 legs of the lander, if it sits on any of the craters or on the boulder, it can topple. So you have to make sure you are on a flat surface. Before Chandrayaan-3, our ability to know that region was limited by 5-meter resolution images we had from Chandrayaan-1 and some limited area data got from other countries. But then in Chandrayaan-3, we had identified almost a 2 kilometer by 4 kilometer area in comparison with 500 meter by 500 meter in the earlier attempt. That means you had a much larger error margin, and we carried more fuel, and we also tested the components in orbit to make sure that this succeeded. And using all these advances, in 2023, when India landed, I'm sure many of you would have witnessed that event itself. And then the lander and rover moved on the surface of the moon. And we also, since we had enough fuel left, we also conducted an experiment where the lander was just lifted up and then again brought down. this will help us in our next activities, where we are going to do sample return mission, and then subsequently humans landing, etc. For all that, this becomes a forerunner. And since we also had lot more fuel left, we brought the propulsion module. We made it come back towards Earth. And then recently, probably you would have seen in the media that one of the findings of this Chandrayaan-3 lander, it had an electron density monitoring instrument. And then it found many information in situ, which is very different from what others had found up to that point of time. And then there are many observations. We had an APXS and also a laser ablation. You fire a laser as the material evaporates, do spectral studies, and based on that identify sulfur was found in this region. So many such things have happened. And then another mission we did is Aditya L1. Probably many of you are familiar that when total solar eclipse occurs, actually scientists set up their experiments in the specific region where you can see total solar eclipse for looking at beyond the photosphere. For the few minutes you get in that time, they work for years together and try to collect data. Whereas this particular satellite enables looking at sun 24/7, and by using that, you can make use of large number of observation capabilities. And here again, it is at a very unique point called a Lagrange point. Between two planets, between Sun and Earth, there are specific points where if you are able to keep an object with very limited energy, you can keep it there for long periods of time. So India puts Aditya L1 in a point called Lagrange L1 point, and using this over last 2 years, we have been collecting data. And recently, it also made a huge impact by working along with other planetary observing systems which are there and trying to determine the effect of coronal mass ejections and how it is going, how it can have impact. Many of these studies are going on using this. And another very interesting experiment that India started doing in building its own capability is using our fourth stage of a launch vehicle. In the earlier periods, this stage was simply moving around Earth and then finally come down and land on maybe water or some ocean. So what we started doing is we made use of this platform for conducting experiments so that later when we build our space station, the experiments can be forerunners for that. So using this, we did an experiment which is very interesting, what is called as a crops. So you will see in this particular slide how seeds sprout, and then as the seeds sprout, this experiment was conducted by the orbiting platform, and then over a few, it was there almost for 90 days, and then you will gradually see seeds sprouting. That means conducting experiments of how seeds grow in space, in microgravity, etc. So we tried to make use of a spent stage of the fourth rocket and made use of it as a forerunner for our space station. So you can see now leaves emerging, and then this particular experiment was carried on our POEM platform, and this platform is also used for large number of experiments to be conducted by student community and other researchers. And then over this period of many decades, India has done more than 236 missions. We have 4 types of launch vehicles, PSLV, GSLV, and then making use of cryogenic engines. And we have small satellite launch vehicle, which is capable of putting small satellites into orbit. And then starting from sounding rockets, which were initially brought in the form of kits, gradually built the capability, and today you have not only launched satellites built by our own country, but more than 400 satellites of other countries. And this year we are also, very soon, you will also see the launch of Bluebird in a commercial basis. And while you are doing this, you are also improving your technological capability of doing reusable launch vehicle development, etc. And then if you see the overall journey, starting from 1969, in fact, early this year, we also did another experiment, what is called as SpadeX. That means 2 satellites orbiting in space, moving at a velocity of almost 7.5 kilometers per second. 2 of them can come together and dock, undock. So these are all precursors to our requirement of human space station activities. And India has moved progressively starting from 1969. And today it is among the few countries in the world which is capable of using space technology with an indigenous capability of launch vehicle, satellite application. And what is ahead? India is looking to provide the capability of taking humans to space, Gaganyaan. While the original objective was by the 75th year of independence, we should have put Indians into orbit. But because of COVID and many other issues, it has got delayed. But in the next couple of years, you will see Indians going around the Earth by our own launch vehicles. Of course, this year you saw Shubhanshu Shukla going to space using the Axiom's launch vehicle and then reaching the International Space Station. Earlier to that, Rakesh Sharma ji had gone way back in '84 with a Russian launcher and Russian space station. And then what India is trying to do is, space economy is going to be $1 trillion economy. A country which has an end-to-end capability of building launch vehicles, satellites, and making use of it for various applications, should it be constrained, or should it also be a big significant player in the global space economy? So the government of India is moving ahead, is making the space technology accessible to the operators in the country, private entities, and it's opened up, changing its policies, and it has set up New Space India Limited and a center in National InSpace, this Space Promotion and Authorization Center. Using this, it is enabling the country to participate in space activities in a much bigger manner. Today, more than 500 MSMEs and 50 large companies are involved. More than 200 startups are there. In fact, today there are private companies which are trying to build launch vehicles. Probably very soon, in a few months' time, you will see one of the first launches by a private company in the country. Both ISRO and InSpace is trying to promote this capability in the country, and many companies are building their own satellites and applications. All this is going on, and this is happening through basically 3 segments. ISRO concentrating on space technology, space research, New Space India Limited making use of the national assets in space and then ensuring that it will continue to operate there, and a regulator plus promoter in InSpace. With these 3 things, India is actually trying to promote more and more space activities by enabling the not only import substitution and then response programs, research grants to industries, cooperative programs, space-based application research, and then comprehensive space education. There are a large number of activities are going on to enable more participation. And then if you look at how it is going to move ahead, that from LEO to Moon to near-Earth activities and then Mars, all this is the activities that are planned in the coming decades. And then the way you are looking at is India plans to put its own humans into space by this year or by 26 or 27. And by 2035, we will have our own space station operating called Bharatiya Antariksh Station. And by 2040, landing on Moon and then bringing back safely our Gaganauts is the action plan. And if you see in all this, how India has started doing its various activity, probably many of you would have heard of a term called leapfrogging. That means Sarabhai's vision was, how can we enable India to leapfrog into the future through adoption of appropriate technologies. Like I pointed out, when humanity got a new technological capability of going beyond planet Earth, while others were looking at how it can be used for their dominance or military aspects, India looked at how this technology can be used for enabling development, providing broadcasting, communication, connectivity, Earth observation, monitoring, navigation, and a whole lot of applications. And using technologies that were accessible to that, you make use of it. What is not accessible, you build yourself. For example, the cryogenic engines, while one superpower was ready to give you, another superpower ensured that such a transfer does not happen. It became a blessing in disguise, because today you have more than 3 versions of that cryogenic technology being indigenously done. And 1975, India demonstrated how technology can be used in a developing country for improving its communication and broadcasting capability. It was the first of its kind done at that point of time. And then between 95 and 99, India in the civilian domain had the highest resolution imaging system, best in the world at that point of time. And similarly, when the Mars mission was done, it was a maiden attempt in which the country demonstrated that you can reach Mars and orbit Mars. And similarly, in AstroSat, a UV telescope, which is better than the best available at that point of time in that wavelength region. And then 104 satellites were launched in one go using a launch vehicle. All this demonstrated that this capability. Now, what is this leapfrogging as a concept itself? So you can see that if you have to reach a height, if you have enough length available for you to run, you build enough momentum, and then after building the momentum, you are able to take off and jump. What if even that much space is not available for you to develop that energy? So that is where, like a frog, crouch, conserve all your energy, and in one go achieve a height. So that is the kind of thing what is leapfrogging. So what India did all along is, when it had restrictions of access, and also space technology, as you can imagine, is a dual-use technology. Information is not easily accessible. But then what is accessible you use, but use it for solving the problem you are facing, not for simply mimicking what others have done. That is what India showed in the space technology arena. And here you can see some few very interesting statements which we can actually, Dr. Sarabhai had said. The important ingredient for satisfactorily meeting the challenge of the changing environment is not experience, but an ability to learn. Experience is less relevant than knowledge and the ability to learn and innovate. Actually, I would like to quote one example. When Dr. Sarabhai was given the task of running Ahmedabad Textile Industrial Research Association, whose task was to solve the problems of textile research companies, mills, which were using a lot of machines, and then they were looking at how to improve. So he had put an advertisement in the paper which said, people with experience need not apply. It looks so counterintuitive. But then if you really realize, that is a real thought process of today also. If you see, things are changing so fast. What was good yesterday is not going to be okay for tomorrow. That means you have to unlearn and relearn. And you have to solve problems, nature of which you are not aware. So here, your ability to learn makes it more important, and your ability to address problems with a fresh perspective becomes more important. So you can visualize that such was the great personality who could visualize such things way back in time itself. And then another statement you can see is, this is Sir C.V. Raman, technology is not an objective to be aimed at, but a tool to be used for the common man. That means what we need to appreciate, what is the purpose of the activity that is being done today itself, if you look at why all of you are being brought together and being showcased something. Science and technology is the way to address the problems. And then if you have to address the problems, what you are encountering, not only should you learn and then find a way of applying what you have learned to problems you are facing. See, India is aiming to reach by 2047. We are the 4th largest economy today. And if I ask you, what is it that we want to be by 2047? Where you want India to be at that time, what would you say? Where should India be by 2047? Anybody wants to answer? Do we want to remain at the current position, or we want to go down, or we want to be dominated by others, or by controlled by others like what happened in the past? What do you think should happen? By 2047, where should we reach? Nobody wants to answer? I'm sure each one of you have some thoughts. What do you think where we should be? Go ahead, tell. Why are you hesitating? Where should we be? Yeah, correct. At least we should not be dominated by others. While you may not want to dominate others, at least you should not allow others to dominate you. If you should not allow others to dominate you, you should be competent. You should be competent enough to live in the contemporary world. See, if you look at the history of mankind, all the time, what the human being is doing is actually enhancing the capabilities that he has got. He arrives in this world with 5 sensors, 5 actuators, and an asli intelligence using which the system is operating. And as you can see, each one of these features we carry has a limitation. Our eye can see only between 400 to 700 nanometers. But today, how many gadgets humanity has created to showcase to you what is happening in this world? You saw other animals or other life forms seeing beyond the visible light. So today you have built infrared cameras, you have built radars to show you what is happening in nature within the limitations of your eye. That means you have enhanced your capability to observe nature. Similarly, if I ask you, you can walk few kilometers an hour, but then you saw so many other life forms moving much faster than you. So what did humans do? They started domesticating it, riding them. And then you saw birds flying. So what did humans do? Today they have built aircraft, rockets, you are going beyond. That means all the time humans are trying to observe nature and through that enhance their capability to live a better life and then move ahead. But then in all this, it is your ability to observe and translate what you are seeing as a concept in nature into reality. For example, when you are visually seeing sky, today you have built telescopes, you have taken telescopes beyond Earth, and you saw like that. Every activity that humans have done so far, the concept exists in nature, and human being is only trying to bring it into reality. So it is here, every one of you have tremendous opportunity. All of you have come to this world with an asli intelligence, which is so powerful, we are trying to mimic it in artificial intelligence. But if you realize the capability of your asli intelligence and look at nature, you will find enough inspiration to create things which others have not visualized so far. There is so much to do in this world. Every time a new discovery happens, there is a new opening of the window. And what is being attempted in an activity being organized here is showcase to you, to the experience of others, what has happened so far. But then it is for you to take it forward, and opportunity is enormous and tremendous and limitless. So you need not be worried about so many things have already happened, people have done this, people have done that. There is so much more nature is showing which has not been actually mastered or not brought into reality. So all of you have a tremendous capability. I'll end my talk with just 2 points. See, each one of you, when I say you have tremendous potential, I came across a girl whom I met first time. She was 13-year-old. She had already conquered 5 of the 7 topmost points in the world at that point of time. And she had promised herself by the time she becomes 15, she would conquer even Mount Everest. Some of you would have read in the last year's papers, Kamya conquered Mount Everest. Though it did not happen at 15, but then she made sure by the time she was 16, she had conquered all the topmost points on planet Earth. And similarly, there are people who can do, actually, they're born blind person who can answer any question you ask, 10-digit by 10-digit addition, subtraction, multiplication. He will answer. You saw a very young person becoming a chess champion, a 100-meter runner doing it in 9.2 seconds. That means every human being has tremendous potential. All of you intrinsically carry this potential. If you become aware of yourself, aware of your capabilities, how you are operating, how you are a highly evolved robotic system, you can outbeat anybody else. So let me take this opportunity to compliment the organizers of this program to bring such rich information set to you and remind you of the capabilities that you have and tell you that India wants to reach what you want to achieve by 2047. If you make up your mind, nothing is impossible. Thank you very much.
Thank you. Thank you very much. What a beautiful and inspirational presentation. We have 5 minutes time to take question and answer. Anybody has question to pose to Dr. A.S. Kiran Kumar, I request you to please show your hand, and we have mics going around. Ask the questions. Yeah. Anybody? Yes. Can you just give him the mic, please? And I also request all my coordinators at different venues to continue with their own programs.
Sir, good morning, sir. Sir, what is the source of energy in the sun? Can it be artificially created on the earth for a need of energy requirements?
In fact, that has been the attempt of scientists. Fusion is said to be the source of energy in sun. Now, attempt of creating by fusion is being done. A large number of scientists are working on that, but still it is far from reality. But definitely with the further research into that, human being is trying to replicate how the energy is being created in these stars by fusion, and then make sure China is said to have gone significantly ahead. In India also, if you take IPR, that is the Plasma Research Institute is trying to do. So there are many countries and many research groups are working on this problem.
Okay, anyone else? Yeah, I think there is one more here.
Hello, mic check. Very good morning, sir. So my question to you is, ISRO is known to doing missions at such a cost-effective manner in first go. So what is the thinking process which goes behind every mission at ISRO as to how we are so good at utilizing all the resources which are provided to us, and how we make it a point that we are successful in the first attempt itself?
Yeah, see, one of the key things is, like I said, when a new technology became available, what was the thought process? We were a country struggling to provide food, shelter, education to its people. Resources are very limited. And then priority is definitely not space technology at that point of time. But then the people who visualize this were looking at how, in spite of the resource constraints and the limitations you have, how can we make use of a technology to deliver? So you saw step-by-step communication, broadcasting, weather monitoring, and then Earth observation. All this became a reality. So the answer to your question is, if your actually desire is strong enough to provide solution to the society, whatever limitations you have, you can overcome. And it is not that in every event, first time ISRO has succeeded. In fact, many of the first attempts have been failures. Our first launch vehicle, first attempt was a failure. And even like that, if you look at, we have encountered failures. Like what I pointed out to you, you are trying to go do activity well beyond your capability. Capability in terms of what knowledge you have, what skills you have, what resources you have. But still, desire is very strong. And when that strong desire builds a bonding among the people who are working, and then they are ready to overcome many other limitations. They are ready to work 24/7, and do repetitive actions. And it is through such attempts that success has come. And it is not that everything has been done in the very first attempt. And in terms of cost, if you are looking at, what I would like to point out to you is what India has spent in space program so far. If you add up all the money, including adjusting it for the value of the money, that means 1 rupee in 1960 is much different today. If you add up all that, it is less than a fraction of 1 year's budget of superpowers. That means what India has done with its limited resources, it is trying to provide solutions to the problems it is facing. Here the desire is not to showcase, I am also capable of going to space. It is basically the desire is, how can we solve our communication problem? How can we solve our fisherman's problem? Or where a borewell has to be drilled, like that. So when your desire is strong enough to provide solution, many limitations you are ready to overcome, and you actually sacrifice many other requirements of yours. It is this culture which has enabled the organization to demonstrate that resource constraints need not be a limitation in what you want to achieve.
Thank you. Thank you very much, sir. It was, wow, it's a great one. Yeah, so due to time constraint, I may not be able to take more and more questions, but sir is here till 1 o'clock. You may personally meet him and ask if there are any questions. May I request the Secretary, Science, Technology and Waste Management, sir, to come and felicitate Dr. A.S. Kiran Kumar by giving a Kunbi shawl, which is an indication of Goan artisan. May I request, sir? Thank you. Thank you very much, sir. Thank you. Yeah, so we are now getting into a second presentation. Again, it will be, again, it's an exciting lecture by none other than Dr. Anil Kakodkar, sir. So just to introduce, sir, Dr. Anil Kakodkar, born on the 11th November of 1943, joined the Baba Atomic Research Center in the year 1964. He became the director of BARC in the year 1996 and was the chairman of Atomic Energy Commission and secretary to the Government of India, Department of Atomic Energy. During the year 2000 and 2019, he was the DAE Homi Bhabha Chair Professor during January 2010 to January 2015 and INAAE Satish Dhawan Chair of Engineering Eminence during January 2015 to 2017. Currently, he is AICTE Distinguished Chair Professor. Dr. Kakodkar has been is a key contributor to India's strategic programs. He was amongst the chosen few involved in the first successful peaceful nuclear explosion experiment that India conducted way back in 1974 at Pokhran. And later, he played a key role in the series of successful nuclear tests conducted during May 1998, and again at Pokhran, India, also demonstrated nuclear submarine power technology under Kakodkar's leadership. Welcome, sir, and I request all of you to welcome sir with applause. Sir is speaking on India's nuclear energy mission.
Well, after that very interesting and engrossing lecture by Dr. Kiran Kumar, many aspects of my job are become easy. we heard how a passionate application of mind can lead to solution of problems that face our country and do things differently as compared to what others have done, do things cheaper, better, in a more distinctive way, and so on. So, what does that mean? You know, we normally have a tendency that we talk about many things, ideas are in plenty, but when it comes to really doing something with those ideas or taking those ideas forward, there is a bit of risk-averse tendency. And we always look for, has somebody done it? Then we can follow. Now, I only want to suggest to all of you, my young friends, that if you want to be a good follower, then by definition, you can never be a leader. So you don't want to be always a follower throughout your life, right? You want to give expression to whatever special aptitudes, special insights, special capabilities that you possess or that you are developing. And if you want to now be a leader in your field, then while learning is of course very important, learning from our own experience, as Kiran Kumar, learning from failure is extremely important. Learning from our failure, learning from others' failures, learning from others' successes, they are all very important. But you must not hesitate taking the first step yourself, even though nobody has taken that step in the past. And that is important for all of you, and that is important for the country. So in my presentation, although I have spoken to you on earlier occasions, you means similar occasions, so some of your colleagues, maybe some of you were there last year or year before last. But I still thought that now that Government of India has defined this nuclear energy mission, you must have heard that in the budget speech this year, 100 gigawatt nuclear energy mission. And the legislation, enabling legislation in atomic energy is currently under discussion in the Parliament. It has been passed in Lok Sabha yesterday. It will go to Rajya Sabha. Maybe it is under discussion in Rajya Sabha right now as we speak. So there is that determination on part of our country, India as a whole, to grow atomic energy. And so I thought it's important that we rediscuss that issue again as to what is the challenge, why do we have to pursue atomic energy, and to some extent, what should be the roadmap that we should be talking about. So that's broadly what I'm going to talk to you about. Now, see, two basic things, energy and materials, that determine everything. You heard exploring frontiers beyond Earth, space, and beyond. And there was a question somebody asked, what kind of energy you require. So energy is very important. Energy is important for our day-to-day existence, day-to-day activities. Energy is important if you want to make economic progress, because without energy you can't have economic progress. And now, where does energy come from? It comes from various sources. And I will talk about it in a moment as to where does atomic energy fit in meeting the energy requirements that mankind has, or in India as a country we have. And then materials are important. Many times materials are source of energy, but many times or more often materials are also important for meeting our day-to-day needs. The house in which we live, the clothes we wear, the food that we eat, the so-called roti, kapada, makan, they're all materials. And so you require materials in different forms, you require energy in different forms, and of course energy and material are related. You must have heard about the famous Einstein's equation E equal to mc square that connects material and energy. Now, why I am saying this is the traditional, conventional energy sources. It could be water falling from a height, it could be burning of coal, burning of oil, burning of gas. These are traditional energy sources. Even now, most of our activities are dependent on that. And maybe it will be so for quite some time. And at the same time, we are sort of, on one side, the sources are finite, because, the total materials available on earth are finite. And we have been using it, some people are using it more extensively than others. So many of them have, there is always a peak. Energy use keeps on rising for a particular form. It reaches a peak and then declines. And many times ago, long time ago, for example, forest wood was a very important source of energy. Even today, some people use that, but we say, no, we must protect forests. We don't use that energy. So we have shifted, or by and large, we have shifted away from that form of energy. Today, we're talking about coal, oil and gas. And of course, there is a question of finiteness even there. But a new problem has arisen by their use, consumption or by their use. And that is, you burn these are all fossil energy sources. And by their burning, by their use, you end up in emitting carbon dioxide into atmosphere. That causes global warming, and I'm sure you have heard a lot about global warming and the consensus around the world that we should now reach a condition where there is no net further addition of carbon dioxide as well as other greenhouse gases, the so-called greenhouse gases. And so we have to shift away from that so that further global warming does not take place. So comes the importance of renewable energy. You have solar energy. We are all very familiar with that. Country is very aggressively pursuing solar energy, wind energy, hydro energy is also renewable, both small and large. And so there is a rightful emphasis on continuously enhancing the use of renewable energy. Now, this is where, if you now look at in India specific way, we should look at what are our energy needs, how much energy can come out of renewable energy, and is that enough for supporting our development, or we require much more than that to be a developed country, the Vikasit Bharat. And if you require additional energy beyond what can be provided by renewable energy, then of course the alternative is to take recourse to nuclear energy. And of course, whenever you use energy, there is certain mass deficit somewhere, either here or in the sun, wherever it's there. But if you can make that question, there was a question, can you produce, the way sun produces energy, can we produce that here on earth? And the answer to that, Dr. Kiran Kumar did give, there is work going on. But the fact is that if you can consume some of the mass to convert that to energy here on earth, then you open up a huge source of energy. And in fact, the question about finiteness of earth resources, of course, in absolute sense, that question will always remain. But the resources, the materials which appear, which are always finite, they appear almost close to infinite. You get access to a much higher energy, and you can do that by way of fission energy, and that's happening today. And as the question was raised earlier, you can do that by way of fusion energy. I'm sure that will happen in near future. So, so you can have access to abundant energy, and important point to note is, in so doing, you don't emit carbon dioxide, or for that matter gases, which lead to global warming. There are of course other concerns. People are scared about radiation and things of that kind. So I'll talk about that at the end of my talk. But the fact still remains that you can get access to abundant energy. And India is on that steeply rising part of that curve. You want to be a developed country or a Vikasit Bharat, then you should really belong to these countries which are represented by those blue triangles at the top, which are more or less a horizontal line. Those are the countries which have maximum human development index. And to be Vikasit, you should reach at least the minimum energy which will take you there. So that threshold where the steeply rising vertical or near vertical line meets the horizontal line. And if you say that you must have that kind of per capita energy consumption, multiply by the population of our country, or say the stabilized population of our country, the sum you will get is 28,000 terawatt hours of energy. This is as simple as that. Now, to give you a feel, how much is that 28,000 terawatt hours of energy annually? The total potential of renewable energy, solar, wind, hydro, biomass, all put together, is around 8,000 terawatt hours. So, the point to note is, to be Viksit Bharat, our energy needs are a few multiples of the total renewable energy potential that we can have on Indian landmass. Today we are using around 9,000 terawatt hours, so roughly comparable with the renewable energy potential. But you can meet current requirements, but you want to be developed, you must use nuclear energy in a big way. That goes without saying. And that's the basis of the nuclear energy mission that has been launched. Now, so that underscores the importance of nuclear energy. Now, let's come to the demand side. After all, we know now that between renewable and nuclear, we can produce all the energy that we require without the concern of global warming. But on the demand side, what are these? You require, of course, you require energy in the form of electricity, but you also require energy in the form of heat. Even our cooking, we can use an electrical gadget, you can also use, or in fact, more often than not, you require a gadget, a gas, or some other form of cook stove, depending on biomass, depending on oil, coal, whatever. So heat as well as electricity are the two basic forms in which we require energy. This is true for our households. This is true of our agricultural fields. This is true for transportation. This is true for running our industries. So now most of the renewable energy forms, except the solar thermal, for example, or biomass, the energy that you get is in the form of electricity. It was not like that earlier. The coal, oil, gas, it would first produce energy in the form of heat, and then we used to convert that to electricity. Now, the availability of energy in the form of electricity, in proportionate term, if you go to clean energy transition, is going to be larger compared to earlier, which is a good thing, because higher consumption of electricity in relative terms is actually a measure of development. As you develop your economy, as you develop your society, you will find you tend to use more and more electricity. It has happened in our kitchens. It has happened in transportation. Now people have started using electric cars. It is happening in industry compared to old industries where you used to have some boiler and a belt and mechanical wheels running everywhere. Now you have an electric motor and you feed electricity and you do things in a neat way. So that's in the right direction, but that's an important part that we should recognize, that when you say it is not just question of producing electricity or producing heat, you have to go through a whole transformation in the demand side or the consumption side. And when we talk about energy transition, there is merit to looking at technologies across the whole domain. There is a lot of things going on in the context of batteries. There are a lot of things going on in the context of hydrogen, for example. People are talking about fuel cells, people are talking about engines running on hydrogen. So these are all parts of the clean energy, the transition. But they all have to be fed by the sources. And as we saw earlier, those sources are renewable energy. A good part of it will come in the form of electricity. Some part can come as heat, and nuclear. And again, nuclear, good part of it comes in the form of electricity. Some part of it can come as heat. But this is how we need to move forward. There is another aspect of this energy consumption, now talking more specifically about nuclear. See, uranium, and that too a small part of uranium, which is fissile. So nuclear energy can start only from there, because that is the only naturally available fissile material. So any nuclear business today has to start with uranium. Tomorrow when fusion comes in, maybe it will start with tritium or deuterium, tritium, and so on. But today it has to begin with uranium. Now that's only 7 parts in 1,000 of the total uranium that you have. But you can convert the remaining part of uranium into fissile materials in the same nuclear reactor where you fission uranium and produce energy. And if you do that, and that is where conversion or breeding of uranium comes in the picture, but if you do that, then your energy potential from the same uranium becomes at least 100 times bigger. More importantly, just like uranium, there is also thorium in nature. And thorium doesn't have any fissile content, so you don't start a nuclear program with thorium. You cannot. But you can convert thorium to also fissile materials, the way you can convert uranium to fissile materials. And when you do that, you get access to, again, thorium in earth is also an equally large amount. So you get almost, by recycle or conversion, you increase the nuclear potential maybe at least 100 times. And with use of thorium, you make the whole thing double. The 100-time enhanced potential, you make it double. Talking about India, we have very modest quantities of uranium. So all growth we are talking about would have to be based on imported uranium. But if you are able to make use of this aspect of conversion of nuclear materials to fissile content and use that for energy production, then we are custodians of one of the largest thorium deposits on earth. So the energy potential on which we are residing through our thorium endowments is such that we can meet all our energy requirements for at least a few centuries, but we can also meet energy requirements of other parts of the world. And that is the opportunity that we should look at. And I think if I had to state a problem before India, because this is not the situation which will prevail in other countries. Other countries are all glued on uranium, and for them, whether it is uranium or thorium, it is the same thing. So they better stick to uranium because the world has much larger experience on uranium. But we have to make sure that we address the challenges before us. And so we have to move to thorium as fast as we can, regardless of whether world moves that way or not. And this is quite possible. There is, but it's only, again, as I said in the beginning, if you say whether somebody else has done it and then we will do it, then we will never do it. So the important thing is we need to be moving ahead based on our own understanding, our own knowledge, our own learning up to present time, and improve it to go forward. But if you do that, then in fact that's the three-stage program which Dr. Bhabha had chalked up has actually exactly this as its basis. And on the bottom left-hand side of this figure is the schematic of that three-stage program. Now today what has happened is, it was going on, the program had to be developed in spite of embargoes, we lost a lot of time. Although today we are self-reliant, today we are around 9 gigawatts of nuclear capacity. Compared to country's requirement, it is small. And that is where the emphasis has come. But we should recognize that a nuclear plant on an average costs you around 15 to 20 crores per megawatt. So 20 crores per megawatt would mean 20,000 crores per gigawatt, and which would mean roughly 200,000 crores for the program that we are operating. 200,000 crore rupees will be 2,000 crore dollars. 2,000 crore dollars comes to roughly 20 billion asset value that exists. And it's producing 15% return. So you are kind of creating, we're talking about a 20 billion economy already, contributing to roughly $3 billion profit annually. And that's all has come about by our self-reliant development. So we should be very proud about that. Now the question is, 9-10 gigawatts are nothing compared to the requirement that we have. As we saw in the other one, we should be talking about 1,000 gigawatts or 2,000 gigawatts. And that is the basis of this 100 gigawatt by 2047. And that means we have to be able to do 10 times larger than what we are currently doing in another 22 years, 25 years and 47. We have to reach 100 gigawatt by 2047. So that is the acceleration that we need to do. And that is the challenge before the country. And as I said, as we do accelerate, we have to be also mindful of the fuel resources from where they will come. And that has brought importance of two things. One, a very rapid growth, and second, a very fast transition from uranium to thorium. So I personally have been advocating that we should of course accelerate the three-stage program, but we can also think of, three-stage program was to irradiate thorium in a larger capacity of fast breeder reactors to produce fissile material. Now we already have talking about larger capacity of uranium reactors based on imported uranium. So we can as well use that platform to irradiate thorium and produce that. So you can follow two tracks. A track where you irradiate thorium in this enhanced capacity of PHWRs, and quickly move to third stage, that is thorium uranium-233 stage, essentially consisting of molten salt reactors. And whenever fast breeder reactors pick up, they will, of course, supplement this process and contribute to growth. So this is one track. And the second thing, as I said earlier, is to increase the deployment rate, deployment of nuclear capacity to much faster rate. Now, it's not as if this will cost you a lot of additional money. Quite the other way. This will actually give you some savings because thorium has that advantages. Now, you can all Google this and find out, or look at the textbooks and find out. But with thorium, and particularly if you irradiate a combination of uranium, thorium, you will get more energy per unit of mined uranium. So you get some saving there. You get saving in terms of spent fuel management, and you get a lot of advantages in terms of safety. You get advantages in terms of proliferation. There is no fear of proliferation if you use thorium, because whatever comes out of such reactors, you cannot divert it for weapons purposes. No way. So this is actually a low-hanging fruit we should move forward to. So with that, what should be the elements of our nuclear energy mission? And of course, we have this PHWR technology. We have many of them operating, well-proven technology at 700 megawatt capacity level. We also have them at 500 megawatt capacity level and also at 200 or 220 megawatt capacity level. And I think all of them have their own niche area. The bulk has to come in the form of 700 megawatt reactors. And just to fix some numbers, if the entire 100 gigawatt has to come out of these 700 megawatt units, then you will require 100,000 divided by 700. So you can calculate how many reactors have to be built. And that has to be done within same 22 years. So you should be building like 7, 8 reactors every year to reach that capacity. So you need more institutions. So now, in addition to NPCIL, NTPC has become a player. There will be other entities which will come, they will be, but maybe even private entities should come in, and the new bill would enable that happening. But this is very important because I think there is no way a single enterprise will be able to build so many reactors at one stage. So we have to do capacity building of all these industries. So what I'm trying to say is, on one side there is science and technology, but other side there is program, implementation and management. So some of you, depending on your aptitude, I think there is scope for people with different aptitudes. And then we should think in terms of moving forward with thorium in these reactors. Once we do that, I think it becomes a fit case for India to export these energy systems, because the world also will have similar. So instead of our trying to follow, once the world recognizes that this is a beneficial thing, this is a cheaper alternative, I think we have that potential to provide energy for the rest of the world. Even after that, I think there will be scope for additional implementation, additionality in implementation. And so we should have space for imported systems, although provided they meet all the safety requirements and they meet all the economic competitiveness criteria. And then we should, while we accelerate this, we should accelerate our development towards breeder reactors, towards thorium reactors. And because rapid scale-up requires standardized design, and new development requires a lot of innovative work and sort of stabilize the design so that that also becomes standardized and you can take up for rapid multiplication. I also see a day which is not far off when you could have small reactors, the so-called micro-modular reactor. So you have a complex and maybe a 2 megawatt system or 5 megawatt system right sitting in the basement, whether it's a housing complex or a commercial complex and all. It is quite possible. People are talking about what is called walk-away safe reactor. And I think that's a space for a lot of startups. Young people, you can design your own plants. Of course, you have to deal with the government in terms of fuel supply. But that, I think, is a distinct possibility. So I come to the last slide and the last statement, and that is, I said that nuclear doesn't lead to carbon dioxide emission, but there are apprehensions. People are scared. Chernobyl happened, Fukushima happened. So I have picked up a newspaper story on Chernobyl, and I'm going to just read out to you. The Chernobyl story as a catastrophe is a farce by any account of reasonable and rational introspection. I'm not saying that. That reference is there. That journalist has gone around, and I suggest that you can also Google yourself and figure this out. You can now take a Chernobyl tour. You know, like you go to many places for sightseeing, you can go to Chernobyl. You can take those tours. The wildlife is thriving. Reactor 1, 2, 3 are continuing to operate because that accident took place in unit number 4. After unit 4 went offline, and they went on to provide enough energy for 2 million homes, or about 5 million people. Now, don't feel very surprised. These are facts. Unfounded fears related to security as well as radiation have resulted in much of developing world remaining deprived from the benefits of nuclear power. And again, as we said in the beginning, rather than depending upon whether somebody has done it, what somebody else says, I think we should take these decisions ourselves based on our own understanding for our own benefit. And I will stop here. Thank you very much.
Yeah, thank you very much, sir. It's indeed very, very interesting. Yeah. We'll take maybe 2 more questions. Anybody has questions to ask to Dr. Kakodkar, sir? Yes. Can you give her a mic, please?
Hello. Good afternoon, sir. Sir, in such nuclear energy missions, what do you think are the limitations, or what limitations have you faced in India, and how have you overcome it?
Well, what we have overcome are the technology challenges. I think there are no technology challenges. We are completely self-reliant on that. What we need to overcome are the implementation challenges. You know, that's where. See, we have built, I think there are 24 reactors operating in the country. So there is enough experience. But the question is, can we build 6 reactors every year? Can we build 10 reactors every year? What about safety? Nuclear technology is an unforgiving technology. So how do we conduct ourselves that we are not only first time right, but everybody is right first time? So that's, so it's a different discipline that we need. So that's, we need to organize ourselves to be able to do that. Bigger problem is finance. All this means money. And I think it is unthinkable that we will be able to find government budgetary sources for doing so. Now, can we depend on private capital? Can we trust private industry to do a responsible activity? Now, all this is possible. One can say there are most of the world private entities are working. Where is the problem? But then we also see Indigo, current. So there is some learning. So since you are asking challenges, these are the challenges. And I'm sure those can be figured out. And the bill that is there before the Parliament does at least makes a beginning in addressing those challenges. Okay?
Thank you, sir.
Thank you. Anyone? Yeah. Thank you very much, sir. May I now request the chairman of the Manohar Parrikar Vidnyan Mahotsav, Sri Narona sir, to felicitate Anil Kakurkar sir with the shawl. Sir. Thank you very much, sir. Now we have the third technical session, which is being delivered by the recent recipient of Manohar Parrikar Yuva Scientist Award, Dr. Sai Gautam Gopalakrishnan. We already have introduced him. Now I want to introduce him as a recipient of Manohar Parrikar, third recipient of Manohar Parrikar Yuva Scientist Award. Dr. Gopalakrishnan is the associate professor teaching in a very renowned institution called Indian Institute of Science in Bangalore. I request Gopalakrishnan to please take over.
All right. Is it possible to use the pointer that is built into PowerPoint? I think I duplicate. No, but this won't work because it's an LED screen. PowerPoint itself has a pointer. Just slideshow. So thanks a lot for the introductions. First of all, I would like to thank Dr. Anil Kakurkar, Sri Jose Manuel, and all the members of the selection as well as organizing committee of this Manohar Parrikar Vidnyan Mahotsav. It's a privilege and honor to be given this award. The first talk was on space. Very large length scales. Second talk was on nuclear energy, very small length scales. I'll try to be the bridge in between. So I'll try to talk a little bit about how materials sort of govern different technologies, are the key bottlenecks for different technologies, and how sort of machine learning can sort of help in designing newer technologies. And just as a final note, I'm a metallurgist by training, so it's an honor to be part of this Mahotsav, which was envisioned and is now in memory of Manohar Parrikar, who is a metallurgist by himself. So it's good to have that connection as well. So with that, let's get started. Yeah, and just to acknowledge the people who have done all of the research work. So this is my research group, which was about 6 months back. There's been a few changes in the research group. All the funding agencies and the supercomputing resources that we typically use for our research. So I'm a professor of materials engineering, right? So I see a lot of students, school students in the audience. You may have learned physics, chemistry, math, biology, computer science. You may be wondering, what is materials, right? What is material science? What is materials engineering? So let's start with some technical definitions and we'll take it forward, right? A material is typically a substance, right? Typically a solid, and we intend to use it for some engineering application, right? So if you take the case of your cell phones, for example, you have a display. The display works because there are certain materials that have certain properties that enable that display, right? Same thing with your electric vehicles. Your electric vehicles work because they have good batteries, and those batteries work because they have good materials within them. So every application, every device you use has materials that power those devices. So the study of materials, or material science, or materials engineering, is basically a very applied field. So it has lots of intersecting physics, chemistry, biology, math, and computing aspects as well. So I'll give you a few examples of what kind of materials you sort of encounter on a day-to-day basis. I know we use LED lamps these days, but if you ask your parents or grandparents, they would have used these tungsten filament bulbs. These are yellow, they emit yellow color. Just to give a sense, right? So this bulb gives out light because of the unique properties of tungsten, right? So tungsten has a lot of resistance when you apply potential difference across its ends, and due to the resistance, it's able to emit sort of radiation, visible radiation. But the thing is, tungsten is one of the highest melting elements that we have, right? So it's actually very difficult to get tungsten in a very small filament form like this in order to make this bulb a reality, right? So getting tungsten into that form took about 3 decades of work, right? And who did all the work? It's basically material scientists or materials engineers who did that work. I'll also give other examples of other applications. So if you take the case of lithium-ion batteries, so lithium-ion batteries are the ones that power your electric vehicles, your tablets, your laptops, and so on. These devices work because of the unique properties of the electrodes that constitute these batteries. So these electrodes act like solid sponges. So depending on how you apply, what kind of potential you apply, they either absorb or release lithium ions. So these are like solid sponges or ionic sponges, and it's the discovery of those materials that enabled lithium-ion batteries. There are also innovations that happen in the sort of classical metallurgy domain. So if you think about infrastructural applications, we need to produce steel well enough in high quality and also in different morphologies. So that's also a field of innovation that a lot of materials scientists work on. If you think about the production of turbine blades that power aircrafts, I know the aircraft industry has gone through a lot of turbulence recently, some man-made, some natural. But we still need the aircrafts running, and we need good, reliable engines for them. So that has a lot of materials innovations associated with them. And finally, if you have older relatives, they may have taken hip replacements or knee replacements. So once again, you need good materials that are compatible with your body, that can function as replacements. And this is an example of a liquid material. It's called a ferrofluid. So here, the liquid actually finds or takes in a shape depending on the kind of magnetic field that you apply. So just to summarize, these sort of represents very wide range of applications, right? Where the discovery and design of materials plays a very important or a very key role. So just to give one additional example of a very specific application where materials play a key role, I work, or my group works significantly on batteries, so I'll take a battery example. So if you take the case of one of the electrodes within a battery, right, we call one of the electrodes as the cathode. Cathode is the positive electrode. This usually consists of a transition metal oxide. So what is a transition metal? Manganese, iron, cobalt, and so on. They are all transition metals, right? So you have oxides made out of these transition metals. And these are what are referred to as layered compounds. So if you look at these compounds in the microscope, they appear as very distinct layers, just like graphite. So graphite is layers of carbon atoms that are bonded by van der Waals interactions, right? 7th, 8th standard chemistry. So similarly, your transition metal oxides also form these kinds of layered arrangements. So depending on the kind of potential you apply on this transition metal oxide, it can absorb lithium, right, and form a lithiated version. So this compound now has absorbed lithium and is now a lithium containing compound, right? So if you apply the reverse potential, it will lose the lithium, right? So that's why it acts like a sponge. So you have this cathode material, and let's say you now want to calculate or predict or estimate what will be the voltage that you can get, right? So let's say you use this cathode material, what kind of potential you can get from this cathode so that you can actually use it in a battery, right? So the higher the potential, the more energy you can store within a battery. So you can sort of treat this as a sort of a chemical reaction. So if you are familiar with some thermodynamic principles, these G terms are called what are called Gibbs energies, right? So you have a product, you have a bunch of reactants, you can take the difference of Gibbs energy for that chemical reaction, apply what's referred to as the Nernst equation, and then get the electrochemical potential, right? So this is for one of the electrodes, the cathode. If you do the same process for the other electrode, which is the anode or the negative electrode, take the difference between the two, that basically gives you your voltage, right? So that's the operating voltage in a given lithium-ion battery, right? So the operating voltage in a battery really depends on the type of material you use, right? So the type of transition metal oxide you use. So you see the deep connection between the type of material you use and the end performance that you actually get. The same thing can be extended for other properties in a given battery. So there's potential, which is the sort of potential at which you can extract work from the battery. There's also the amount of actual displacement, right, that you need from your system. Here we are referring to charge displacement. So how much electrons are you actually exchanging with your battery? The more electrons you exchange, the more energy you can actually store, right? So in battery parlance, we call this capacity, right? And capacity is also dependent on the amount of, or on the type of material you have and on the amount of lithium that it can actually exchange when you apply this potential. So this is once again a material property. So we see voltage being dependent on a material property. Capacity is also dependent on a material property. The final thing is rate. So we don't want our batteries to store energy, to store large amounts of energy, and then take 10 years to discharge or charge, right? I mean, you want your cell phones to be charged in 10 minutes now, maybe 5 minutes, right? So that you can shoot your next Instagram reel, right? So we want fast charging capabilities, and if your battery needs fast charging capabilities, then the underlying material constraint is that you need the lithium ions, right, that you are getting by applying this potential. You need these lithium ions to move very quickly within your oxide lattice. So you have an oxide structure, you want your lithium ions are going within the oxide layers, and you want the lithium ions to move very quickly, right? So the faster they move, the faster you can actually charge your battery or discharge your battery. And the rate of their movement, rate of lithium-ion movement, is governed by what is referred to as the migration barrier. So this is once again a material property. So the higher the barrier for migration, for lithium motion, the slower the lithium-ion moves, and the slower your rate capabilities are. So you want this EM to be as slow as possible, and this EM is once again a material property, right? So we see that in one given application, in one lithium-ion battery, all of its major performance tasks, so how much energy you can store, how fast you can charge or discharge your batteries, are all dependent on the properties of the material you use, right? So we can sort of extend this exercise to other applications as well. So I mentioned that for batteries, your energy and power densities are all dependent on the underlying materials, and some of the properties of the underlying materials you use sort of govern these performance metrics. So properties are how quickly your ions can move, so that's ionic mobility, how big your reaction energies are, that determines your voltage, and then how stable your materials are. That sort of determines how long you can use your battery for. So whether you can use your iPhone for 2 years or 5 years depends on the stability of the materials, right? So we can extend this exercise to other applications as well, such as solar cells. So let's say you have a solar cell installation in your home. The key, again, material within your solar cell is the semiconductor that's being used to absorb sunlight. So the working principle is that the semiconductor absorbs light and then generates an electron-hole pair, which is then transferred to the external circuit. And as the electron goes through the external circuit, you sort of can extract work, right, from your photovoltaic device. And that's exactly what happens in your solar cell. So the efficiency of a solar cell, so how well it can actually convert the incoming solar radiation into electricity, into usable electricity, is actually highly dependent on the choice of semiconductor, right? And there are several properties of the semiconductor that dictates this choice, such as what is referred to as the band gap. So the band gap is think of it as the energy that you get or that you require for generating an electron-hole pair in a given material. Once again, how stable that material is. Is it resistant to the formation of defects? So in general, the more defects we have, the poorer the performance. So we want pristine materials that are very defect-free, right? Okay, so sort of to summarize, right? So if you use better materials and materials which have better properties, you can almost always get better performance in whatever application or whatever device you are using, right? So that's why materials design or materials discovery is very important, right? So if you use better materials, we get better performance and better applications. Okay, and I gave examples of energy. So materials also play a crucial role in other technological domains as well. So if you think about healthcare, so like I mentioned about joint replacements, so that's one area where materials play a role. Drug delivery. So if you want lower amounts of medicines to be delivered to targeted regions in your body, you need certain materials for that. And also water desalination. How efficiently can you actually remove salt and unnecessary ions in your water to make it potable? Infrastructure and automotive is the classic area of metallurgies. So metallurgy is a sort of subdomain of material science. And here we want to design better automobiles, better bridges, better rockets, right? And also stealth systems and so on. And then there's also lots of materials that are being used in everyday applications, right? So think about Internet of Things, sensors, flexible electronics, and so on. Okay, so now that I have motivated the importance of materials, what does a typical material scientist or a materials engineer do? So what do I do, for example, right? So the first thing that I try to do is I try to identify new materials, right? And I try to do it for fun, quote unquote, right? And I worry about sort of applications little later. This is what these three guys ended up doing in the 1970s, 80s, and 90s. So they ended up discovering electrodes and electrolyte materials for lithium-ion batteries, right? Without the eventual battery. So they discovered the materials first. The battery came later, right? So you want to identify new materials and identify new phenomena that govern these materials, right? So that's one thing that you want to do. The second thing we typically do is whatever existing materials we have or existing applications we have, we try to improve the performance of existing materials, right? So this graph here shows the sort of gains in efficiency in simple internal combustion engines. So your petrol engines that you typically use on your two-wheelers and cars, and how these efficiencies have improved over the last few decades, right? Most of these efficiency improvements have to do with the fact that we are using better materials to make our engine, right? Not all, but most of the efficiency improvements can be attributed to the usage of better materials. The third thing is, okay, so let's say you have a great material, you have an end application that you want to use it for, but how do you scale this whole process? So how do you find better ways to manufacture, more sustainable ways, more cheaper ways to manufacture, right? So one example here is a fiber optic cable, right? So these are cables that sort of go through our oceans and basically provide us the modern internet connectivity that we all enjoy, right? This fiber optic cable, making this fiber optic cable is no mean business, right? So you have a light fiber, an optical fiber that goes through, and then you have sort of layers of insulation and which protects it from multiple things. So from variations in pressure, from corrosion, and so on. So manufacturing this in a large scale is not a trivial process. So we try to manufacture, process these kinds of complex materials and complex arrangements of materials also. And final thing is we want to prevent or postpone catastrophic failure as much as possible. So this is, the Columbia Space Shuttle disaster, right, which sort of blew up, upon re-entry into our atmosphere. We want to prevent such catastrophic failure as much as possible, right? So if you don't see such news items, news articles, then we have done a good job, right? So these are the types of things that a typical material scientist or a materials engineer does. And just to summarize, right, so as I mentioned before I began my talk, so I said that I wanted to be a bridge, right, between very large length scales, so like rockets, to very small length scales such as atoms, and that's what materials does, right? So we worry about phenomena at very large length scales, right, like corrosion, mechanical failure, and so on, to very small length scales as well, right? So where do electrons sit within a given material so that we can tune the band gap of a semiconductor, right? And we also worry about phenomena that take from picoseconds to years, right? So sort of atoms vibrate at the picosecond level. This is pico is 10 to the power negative 12 seconds, so very short time scales. We also worry about phenomena that take years, right? So that could be construction of a bridge, for example, right? Or development of suitable steels for bridges. So we worry about length scales, very large variations in length scale, and very large variations in time scales as well. And if you take away one message, right, from this talk, so let's say you dozed off the remainder of the talk, but you want to take away one message, that is this. So material science has the most science in any engineering discipline and has the most engineering in any science discipline, right? So it's highly interdisciplinary in nature. So if you are remotely interested in material science, you should take it up, right? There are lots of wonderful challenges to be solved. Okay, with that, let's switch gears. So I'm motivated enough of the importance of materials. So let's now think about where does machine learning come in, right? I mean, so far I've not talked about anything related to machine learning, modeling, computations, and so on. So where does machine learning come in? Once again, the key aspect to understand is that if you think about technological innovation cycles, right, usually the development of technology is a fairly slow process. It takes several decades. So this graph here shows the different technologies that were developed and basically the time it took, right? So in terms of decades. So the blue bars are how long it took for the technology to be invented, and the yellow bars basically stand for how long it actually took for the technology to be deployed. So where end users could buy these from the market, right? So technology development is typically a very slow process, right? And innovation, particularly in the energy sector, right? So that could be energy generation, energy storage, energy transport, is also very slow. It's particularly slow compared to other technologies as well. And the main bottleneck, right, that governs the speed at which you can sort of introduce new technologies is basically the kinds of materials that are required or the kinds of materials that you use, right? So if you can somehow increase the speed at which you discover, deploy new materials, you can actually shorten this innovation cycle and make sure that technology reaches the end user in a faster manner, right? So this is where sort of discovering new materials comes in. So if we have faster ways of discovering new or making materials better, we can basically have faster innovation cycles. So make these time scales shorter. And machine learning can play a big role here, right? Because machine learning can typically act as an accelerant. So it can increase the speed of whatever you do, right? So that could be fundamental research or that could be large scale manufacturing, right? So machine learning can play a crucial role here. And in my talk, or the rest of my talk, I'll sort of talk about how machine learning can play a role in modeling materials or making sure that we predict the performance of these materials in a faster fashion, right? Because that is the key to selecting the right material for the right application. Okay, and this also ties in with the sort of fourth paradigm of discovery. So if you think about how science has evolved, right? How scientific research has evolved over the last few centuries. I mean, in the very early days, we just relied on empirical evidence. So I see something happening, and hence that must be true, right? The second thing is, second paradigm is more theory. So we try to come up with theoretical equations, theoretical laws that govern phenomena and phenomena that we don't really observe empirically, like planetary motions, for example. I mean, we do observe it empirically, but we don't track it every single second or every single minute, right? But we can still predict the trajectories of atoms, satellites, and so Sorry, I meant planets, satellites, and so on. And then the third paradigm is what is referred to as computational science. So where we do a lot of the math on the computers. So we sort of offload our hardcore or very hard to solve computational problems onto the computer and then ask you to give us solutions, right? So that's the third paradigm. But we have slowly but steadily shifted to the fourth paradigm where we increasingly use big data, right? So we generate a lot of data. We look for patterns or trends within that generated data, and we use that to make inferences or decisions on what we have to do, right? So whenever big data is involved, so whenever you have large amounts of data, right, machine learning almost inevitably plays a role, right? Just to sort of summarize this, right? So whenever we think about a research problem, right, so we first state an objective. We find the suitable materials or properties, right, that are important, and then we demonstrate prototype, and then eventually we do technology transfer or patenting, right? So this is the typical workflow that people follow for developing new technologies. And the second aspect of this, right, which is finding materials and or properties, is where machine learning can play a role as an accelerant, right? It can help you find materials faster. Okay, so what are the different types of machine learning that we typically do in the field of material science? So first is what I refer to as regressions, right? So here we try to predict properties for a wide range of materials in a very quick fashion, right? So let's say examples could be, let's say you take iron, right, and you take, let's say, silica, SiO2, for example. So these two are very different elements, compounds, very different entities, but let's say you want to predict properties of these compounds very quickly. So properties could be how stable they are, right? How quickly ions move, right? How strong are their reaction energies, right? When you expose them to other reactants. Those are all properties, right? So we can try to construct machine learning models which can predict these properties in a much quicker and accurate manner. So that's one way where machine learning is used typically. The second way that machine learning is typically employed is using or constructing what are referred to as interatomic potentials. So let's say you have a material in hand and you want to improve the performance of that material, but you have to understand some aspects of that material, right? So you have to construct models that can predict whatever happens to that material in a very precise fashion, right? So you construct one model that works very well for one material, right? And that one model is an interatomic potential, right? In a very brief, simple fashion. So we also try to use machine learning to improve the accuracy of these interatomic potentials. The third one is sort of generating more advanced models. So when we hear ChatGPT, right, we think of generative text. So you give it a prompt and then it gives us back text, right? So that's generation by a machine learning model. In materials, we would like to give prompts and then get a material back, right? And what do I mean by a material back is I want a structure back, right? So I want to see where the atoms will sit and how they will form bonds, right? So that's what I want back. And we are in the process of constructing such generative models for materials as well. And some of the advanced models also rely on language. So they take in principles from language models like ChatGPT and then they try to use it for materials and then use the principles of transfer learning. Transfer learning is where you sort of learn from easily available data and then train your models to be very accurate on data that is hard to come by, right? So we'll touch upon each of these examples in the remainder of my talk. Okay. So when you think about machine learning, right? Machine learning is the engine, and whenever you have to operate an engine, you need a fuel, right? So without fuel, it doesn't run, right? So where does the fuel come from, or where does the data come from for doing machine learning? So typically, when you are in the field of material science or materials engineering, you rely on systematic computational data, right? And this computational data typically comes from what are referred to as density functional theory-based calculations. Think of them as very reasonably accurate solutions of quantum mechanics, right? So you rely on quantum mechanics to come up with the data, right? And most of the sort of databases that you see around the world, so open source databases, rely on quantum mechanical calculations to get systematic data, right? You can also use what are referred to as systematic experiments or high throughput experiments to get data, but such databases are less common because it's just more expensive to run 100 experiments than do 100 calculations. There are also now leaderboards available. So if you are interested in making predictions on one particular type of property, right, you can already see which models are the best ones so that you know where you stand or you know who your benchmark is, right? So there are already leaderboards available now. So the data is now reasonably well available. So if you're interested in using up some of the open source databases, you should be able to construct models based on those databases. So you don't have to spend a lot of effort in constructing datasets or databases by yourself. Okay, and in terms of the tools itself, so as long as you know Python, right? I mean, if you don't know Python, that's fine. But you know, if you are interested in machine learning, Python is the basic necessity. So whatever data organization, whatever machine learning models that you construct, you will typically use Python for. Okay, so how do we, so in my group, design materials, right? So the classic approach, if you think about, is the Edisonian approach, right? So you have a problem at hand. So let's say you want a nice electrode for a battery material. You go to a lab and then make 100 different candidates, test all of them, and then choose one, right? That's the classic Edisonian approach. I like to take the Iron Man approach, right? So where you have a touch screen and then you just toggle some buttons and then you get a material out. I wish my life was as fancy, but it's not, right? So what we end up doing is we do a lot of calculations, basically. So a lot of quantum mechanical calculations, and we do significant amount of machine learning, right, to predict materials that can be good for a given application, right? So this is what we typically do in our research group. Okay, so with that preamble, so I've established the importance of materials for different technologies, and I've sort of motivated how machine learning can be useful in identifying new materials, right? So now I'll give you a taste of how modern machine learning has made a significant impact in materials as a discipline, and some use cases as well, right? So the use cases that I will talk about are how can we predict properties quickly, how can we construct potentials very accurately, or models for a specific system very accurately, and how do we construct some of the advanced models, right? So I'll just touch upon these briefly. In the interest of time, I won't go too much into the technical details, but if you have questions, I'll be happy to take them. Okay, so just to give a preamble, right? So if you think about modern machine learning, it's inevitable that you use neural networks, right? So how do we mathematically sort of think about neural networks? So let's say you have some data that sort of looks like this, right? So you have, let's say this is your y-axis, this is your measured quantity, this is your independent quantity, x-axis. Let's say you have some non-linear data that sort of looks like this. Now, if you want to fit a simple model, the simple model may have difficulties in fitting this data properly. So let's say you have a simple fit that goes this way, then you miss out these two data points, right? And if you have a model that goes this way, then you miss these two data points, right? So you necessarily need more complicated models to fit more complicated data, right? And this is where sort of neural networks come in. So they sort of mathematically look like this. So this is your input, what we call as input node or input layer. So this is where you supply your independent variables, right, that you use for measurements. And then you have a bunch of hidden layers which do some mathematical operations. They have a bunch of weights and biases associated with them, and what are referred to as activation functions, right, that determine whether a neuron is activated or not. And then finally, you have an output layer that makes a prediction, right? So you have an input layer, a bunch of hidden layers, and an output layer, right? That's the simplest possible construction of a neural network. So how does a neural network work in practice? So you sort of have to optimize these bias terms and these weight terms. So these are all mathematical terms that you have in your neural network. And if you optimize them or fit them based on some data, then you get a model, basically, right? And there are also these activation functions. So these activation functions basically dictate how the neurons are connected, what connections are important, and so on. So this is a very simple preamble to a neural network. There are several different types of neural networks. But for materials as a field, there's one class of neural networks that are very important, which are referred to as graph neural networks. So what do I mean by graph neural networks, right? So if you sort of look at a material in the atomic scale, right, in a very good microscope, you will see a bunch of atoms, and then you will see a bunch of bonds that are connecting these atoms, right? So any material can be represented by a structure, right? A structure is basically a collection of atoms, so where they are sitting in space, and the collection of bonds. How are they interacting with one another, right? So you can transpose that information into a graphical form, right? Into a graph network form. So what does a graph network typically contain? It typically contains nodes, right? And then it typically contains edges, right? So this is an example of a graph network. So here, each node basically represents an atom, right? And each edge basically represents a bond, right? So you now have a very straightforward representation of a collection of atoms and bonds into a graph network, right? So this is a mathematically very straightforward representation. So once you have these graph networks built in, you can do what is referred to as message passing. So message passing is, as the name sounds, it's like, you know, atoms sending emails to one another, right? So each atom sends messages to its nearest neighbors. It also receives messages from its nearest neighbors. So each atom gets to know about its neighboring coordination environment. So let's say you have a water molecule, right? So each oxygen sort of knows about its hydrogen, right? And each hydrogen also knows about its oxygen neighbors, right? So you can do this message passing mathematically in a very systematic fashion. Again, I won't go into the details, but again, if you have questions, I'll be happy to take them. And once you do message passing, sort of all the atoms know about all the other atoms, right, within a graph, and you have a perfect representation of the collection of atoms and bonds into a mathematical framework of graph networks, right? Once you have this representation, you can then put that through any neural network architecture, right? So if you combine a graph network with a neural network architecture, which has weights, biases, update functions, and so on, that is basically your graph neural network, right? And graph neural networks are what power any modern day machine learning tool that has been designed for materials. Okay, and these can be used for different applications. So I'll just give you an example of applications where graph neural networks have made a mark. So one is you can predict material properties based on just their structure. So based on the collection of atoms and bonds, right? So one of the very first implementations of a graph network for analyzing materials was back in 2018. So this famous work, where this is basically called Crystal Graph Convolutional Neural Network, or CGCNN. Okay, so using this model, the authors were able to predict a bunch of different properties with fairly reasonable accuracy, right? But this is a classic use case of a machine learning model. So you build a very powerful model, and then you see all the data, and then you learn from all the data, right? This is a classic way of doing machine learning. You can also do what is referred to as transfer learning, right? Which is an even more powerful way of learning, and learning in a fairly quick fashion. So what do I mean by transfer learning, right? So if you sort of think about material science as a domain itself, it is a very data constrained domain. So ionic mobility, so how quickly ions move. We don't have data on lots of different materials, maybe a few hundred materials. How easy is it to form defects in a semiconductor? Again, not a lot of data. And how easy or difficult is it for some molecules to adsorb onto a surface of a metal or surface of an oxide? Once again, we don't have a lot of data, right? In all of these data limited domains, we can use the principle of transfer learning. So what is transfer learning, right? So I'll give you a vision example. So let's say you want to classify images of tumors. So either they are malignant or they are benign, right? But let's say you don't have a lot of data, right? So how do you train a neural network model? Because neural network models typically require lots of data. So what you can do is you can actually download a bunch of cat images from the internet. That's practically cheap or practically free, and you can get very large amounts of images, right? So you download these cat images, train a typical neural network architecture, right, to classify whether an image is cat or not cat, right? So it's a simple classification task. And then once that model is trained, you sort of freeze most of the model. So we transfer the knowledge to a newer model, right? And then we just retrain, or what we call as fine tune, on the target task, right? So initially our model was able to classify cat images, right, where we have, let's say, millions of images. And then we transfer that knowledge, right, where the model now understands how to read images, basically, to predicting, tumorous images which are either malignant or benign, right, cancerous or non-cancerous. right? And this data set may be a few thousand images that you have. So not a lot of data, but you can transfer most of the knowledge, right? So this principle is referred to as transfer learning, right? And as humans, it is actually quite common amongst us, right? So you may have been a trained physicist, for example, but you may be working on hardcore metallurgy problems, or other way around. You could be a hardcore metallurgist and working on physics problems, right? So we keep transferring whatever knowledge that we have gained from one domain to another. So same thing can happen in neural network architectures as well. So we actually use this principle of transfer learning to address a very important data limited property of battery materials. So once again, if you think about battery materials, we need to worry about how quickly ions move, and that is a property where not a lot of data is actually available, right? So we thought, okay, why not try to use transfer learning to see if we can generate good models that can show excellent predicting capabilities for predicting this rate, right? So first what we did was we actually constructed a data set, because a data set is not even available. So we manually constructed a small data set. This data set only has about 600 data points, so it's not a lot. We then used a graph-based architecture. So just like the graph neural networks that I showed you before, we used a similar architecture. We pre-trained it on some easily available properties of materials. And then we fine-tuned, or we transfer learned on the data set that we compiled here, right? The manually curated data set, and we generated models that exhibited excellent performance, right? And these transfer learned models can also generalize very well and can also classify very well. So it can classify whether a material is can have very high mobility of ions, right? Can move ions very well. It can also predict materials that it has not seen at all before very well, right? So transfer learning gives you a lot of this transfer of knowledge, which helps you build more robust models. Okay, so that was on property predictions, right? So switching gears to more intraatomic potentials, right? So once again, intraatomic potentials are usually for specific systems. We want models to be very accurate for a given system so that we can optimize the performance of that system. What kind of optimizations we are interested in? So for example, let's say you are interested in some kind of computing or memory-based tasks, right? So whenever you compute or have memory-based tasks, you need to have a change in your bit, right? So you need to store a bit as 1, or if it is not stored, it is 0. So you need to have this change between 1 and 0, right? These 1 and 0 changes can be induced in a material by applying short electrical pulses. So depending on the pulse you apply, it will change its state so that you can track the change in state very easily. So if it is not changed, it is 1. If it is changed, it is 0, right? But in order to do this in an efficient fashion, we need to understand how much electric field, for example, we need to apply for this transition, right? So this is a material property that we need to quantify, right? So to do this, we need very good intraatomic potentials, right? Same thing in the case of, let's say, catalysis. So catalysis is where you use a catalyst to accelerate some chemical reactions, right? The famous example is ammonia synthesis, right? Which is important for generation of urea, which is a fertilizer, right? So for generating ammonia, you have nitrogen and hydrogen, which do not react very well by themselves. So you need a very good catalyst, right? So designing catalysts, right, we need to sort of understand what kind of materials we use, what kind of surfaces we use, and how these atoms or molecules can actually react on that surface. So to do that also, we need intraatomic potentials. And this is also an example of a catalyst, right? So you have copper gold clusters, and when you have these weird clusters, they have very excellent properties, right? Very excellent electrical properties, which can help you accelerate some catalytic reactions, right? So to do all of this, you need very good intraatomic potentials. And this is where graph neural networks have made a huge dent, right? And now you have networks which have been trained on very large amounts of data, so about 1.5 million data points now. And these models can basically have accuracy or comparable accuracy across the entire periodic table, right? So you can now model any material in a reasonably accurate fashion very quickly. And not just that, you can also predict corrosion behavior of different systems. So this is basically a comparison between model predictions and the actual data, actual computed data. This is corrosion of copper. So how easy it is for copper to corrode under different pH conditions, acidic, basic conditions, and as a function of different applied potentials, right? So we see that the models can actually predict them fairly well. And these models are being rapidly generated, right? So there are lots of very accurate, very good, very robust interatomic potentials being constructed, and all of these potentials are powered by graph networks. So if you use graph networks well, you should be able to construct interatomic potentials well. And let me go to the final example, right? So the final example is what we refer to as inverse design problem, right? So let's say so far, I've been telling you that, for any given application, you need to choose a material, right? Choose the right material with the right property. The classic way we do this is that we consider a wide range of candidates, maybe 1,000 materials, right? We calculate the properties, the required properties of these 1,000 materials, and then we try to identify maybe a few, let's say 3 or 4, which have the right properties, right, for my given application, right? That is the classic approach to materials design. So you have an end property or end application in mind, and then you screen for materials. So you start with a wider range, and then you keep narrowing down your search. That's the classic way. Excuse me. The more modern way would be to invert this whole problem, right? So let's say I have a property in mind. Can I now teach my model, right, to give me back a material which will have that exact same property, right? So I tell, okay, let's say I want to design a good electrode material for a battery. I tell my model, okay, I want this voltage, and then the model will give me back my material, give me back my structure, right? If this were possible, this is referred to as inverse design, right? So you give a property of interest, and then the model gives back the structure, right? And this is now possible with, once again, graph-based architectures using the process of what is referred to as diffusion, right? So I'll give a brief example of what diffusion is. So let's say you have an image, right? Image of a person here. You keep adding some amount of noise to this image. Eventually, you'd see that the image becomes just white noise. Right? More and more noise to the image, right? It will become blurry. It will become blurry, and then finally it will become white noise. So this process of adding noise to an image, to a pristine image, and getting white noise is referred to as diffusion, forward diffusion. If you now learn, or if you teach a model to reverse this diffusion process, right? So let's say you start off with this blurred image here, right? And then teach the model how to de-blur, right? How to recover back your original image, then that process is referred to as reverse diffusion. I don't know how many of you have watched the movie Tenet, but in Tenet you have forward propagation of time and backward propagation of time. Maybe not many of you have watched. It was released right around COVID time. But so diffusion typically happens in the forward time direction. Reverse diffusion happens in the reverse time direction, basically. So we are learning how to reverse time, right? So this process is referred to as diffusion, and diffusion is a common process that can be used in any neural network architecture. So if you use that with graph-based networks, you can now use that to generate structures, or you can create generative models, right? And these models have recently started appearing in literature as well. So there was a recent work on sort of designing new superconducting materials, high temperature superconductors, using this inverse design approach. So once again, you give a property, and then the model tries to give you the right materials that will have that property. There's also work by Google DeepMind, right, in trying to design generative models. And there's also work done by Microsoft in trying to design these kinds of generative models. And all of these models have been powered by graph-based neural networks. Okay? So with that taste of what modern machine learning is doing to material science, I'd sort of conclude my talk. So designing better materials is crucial for improving the performance of several applications, right? And this is where machine learning, alongside computations, can play a very important role. There are also different ways that which researchers and scientists use machine learning in the field of material science. We use it for predicting properties in a quick fashion. We construct very good interatomic potentials, right? And we also do structure generation. We do inverse design, right? But material science is a little different from other conventional engineering or scientific disciplines in the sense that it is very data limited. So you typically have very small amounts of data, which implies you need to be very careful about constructing models, right? So, and it's also important what kind of data you feed into your model. So generally machine learning models are great engines, right? So if you take a petrol engine and feed it diesel, your engine will cease, right? It won't move.
Same thing with machine learning, right? So if you feed in garbage data, what you will get will be garbage, right? So you need to feed in good data so that you get good outputs. And which model to typically choose? I mean, my advice is always to choose simple models first and then try to increase complexity depending on what kind of performance you get. Now, I think this will be an FAQ, or I'm addressing one of the questions that will come up in the audience. What about some of the real success stories? You have shown, these nice examples of machine learning models. Are there real products that we can show? I'd say products are not there, but the materials are there. So we have made materials, we have validated that experimentally. There are probably prototypical stages, developments that have been done, but an end product is not there. But this is a fast-moving field, right? So we will have new products that were completely designed using machine learning models in the near future, right? And this is a very exciting field because there's lots of ongoing work, and it's a very fast-moving field as well, right? There are lots of rapid developments that are happening here. And some general advice. So, so don't do machine learning just because you can. So find a problem, and then if the problem deserves or needs machine learning, then use machine learning, right? So with that, I thank all of you for your attention, and I'll be happy to take questions.
Thank you. Thank you. So we have now concluded all the 3 technical sessions. They were so interesting and very, very informative. As Dr. Sai Gautam said, we traveled from space to the nuclear and also understanding the material sciences, which are actually helping the country grow both scientifically as well as economically. We are also growing as a superpower. Any questions to Dr. Sai Gautam? Yeah. There's one question. I'll take one and another 2 questions because we are also getting a little late.
Good afternoon, sir. Sir, you said that like working on mechanical failures is a part of your profession. So my question to you is, like, what are the problems that are causing these failures, and what are the steps that you can overcome these problems?
Good question, right? So there are several factors that that govern failure. Some of them are sort of engineering factors. So let's say you construct a bridge for 100 vehicles and then you operate 200 vehicles on them, the bridge is going to collapse at some point. So that's an engineering failure. Some of it are material failures. So that's wrong selection of a material, right? In some cases, it can even be the long sort of resonance frequency of a material, right? So we have seen bridges collapse because there was periodic motion of people or cars, right? That coincided with the resonance frequency of a bridge, and then the sort of bridge collapsed, right? So there can be flaws in the materials design as well. And the third factor that typically happens is nature, right? So you have extreme weather events, you have slow degradation mechanisms like corrosion, right? Those can all contribute to eventual failure, right? But as scientists and engineers, we try to predict the failures as ahead of time as possible so that we minimize loss to lives and property as well as possible. That's all.
Thank you,
I hope that answered your question.
Yeah, I think the second question, yes, please go ahead.
Good afternoon, sir. So my question is that just like how we have solar energy, we have geothermal energy. Is it possible, or are there any attempts made to capture lightning energy, like energy which is around, I think, billions of joules in lightning? Is there any attempt made to capture that energy and channel it for any normal daily use, like?
Yeah, I mean, so in principle it's possible, right? So whenever there's an energy source, in principle it is possible to tap it and use it, in whatever application we want. But the problem with lighting is, I mean, if you think about solar energy, right? One of the main problems with solar energy is that it's intermittent, right? So you only get sunlight for, in India you get it for about 11 to 11 and a half hours a day, right? So what do you do in the remaining time, right? So and lightning is even more intermittent, even more unpredictable. So a technology which captures energy from it will not be commercially very feasible. So that would be the main bottleneck. And again, even if you capture the energy, where will you use that burst of energy, right? So you need to find a suitable end use for it. Because if you use like simple electric grids, right, that we have, it will fry those grids, right? So it's not like it's not possible to capture it. It's what use cases we have, and I mean, do we really need it? So I hope that answered you.
Yes, sir. Thank you, sir. Yes,
thank you. Thank you very much, Dr. Gopal Krishna. Now, may I request Professor Sunil Singh to come and felicitate Dr. Sai Gopal Krishnan with Divli. Thank you. Yeah, I also now extend thanks to everyone who is involved in making this 7th edition of Manohar Parrikar Vidnyan Mahotsav a successful event. Beginning with the advisory committee headed by Shri Jose Manuel Nerona and the director of NIO, Shri Professor Sunil Singh, Director NIT, Director IIT. Who have constantly supported with their technical knowledge in making all these events right from the beginning a success story. I also would like to thank all teachers, students who have participated in these events. And it's not just a participation, but also very live interaction that you had, not only in an IO, but I'm also getting feedback from all the 8 venues that we are having. We simultaneously scientists are speaking. We are getting a good response from all of them. The lectures were very good and also a great interaction among them. Thanks to the director DST IW, who has taken keen interest and supervised this event right from the beginning. Every day we used to have a meeting either in the chamber or in GWMC. His guidance has really shaped the path that we are now seeing today. And this is a success. I would like to thank the director, DSW, for that. Also, a special thanks to all my colleagues, young engineers from GWMC, who are just not part of this particular 7th edition, but they are there right from the beginning. And their support in making all these 7 editions are so important, and their energy that you see is absolutely phenomenal. I would like all of you to kindly give them a big clap, because they are the pillars of Manohar Parrikar Vidnyan Mahotsav, and their support is greatly phenomenal. Extremely happy to announce my thanks, especially Mr. Rupesh, who is, I think he's here, who was single-handedly communicated to all the scientists, as well as the advisory committees, and also a committee which is headed by Dr. Anil Kakodkar to select Yuva scientists. His support, of course, it was background, but it was phenomenal. I especially thank Rupesh, if you're here. It was a phenomenal support that you have given. Thanks to everyone who have directly or indirectly contributed in making this event more successful. Thanks to Anil Kakodkar sir, who is there with us right from the beginning when we announced Manohar Parrikar Yuva Scientist Award, and we continue to see you, sir, guiding us in future too. Thanks to Dr. Kiran Kumar sir. It was the last moment that I had to call you, and then he was so happy that yes, Manohar Parrikar Vidnyan Mahotsav. He also said that it's very great that you are organizing something which is in his name, because he has made in his name not only in a political arena but also in scientific and technical fraternity. He is much respected. And sir, I think you have accepted our invitation and you have come here, and your lecture was phenomenally interesting. Thank you very much. At the same time, I also would like to thank all the speakers who have made to this date and delivered lectures in their field of expertise. And I also getting a lot of feedback that it was very, very interesting. And I would like to see you all coming in future to inspire our student. And it's not just inspiration, but also making these students take a path of science and technology in their future endeavor. Thanks to NIO and all the liaison officers which are there with the speakers. Thanks to Dr. Judith, who has been part of this since the beginning, and the liaison officers' contribution in making this event more successful. I would like to extend thanks to all of them. Thanks to everyone, media, press, and also the tourism department, who is constantly helping us in supporting this. And not last, but not the last one, but I would like to extend my deep appreciation and thanks to Vincent Graphic, who is constantly and continuously supporting us in organizing this event right from the beginning. Thank you all of you, and I request you all to join us for the lunch which is served outside. Thank you very much, and safe journey back to your respective colleges and schools.